system on which this webinar is a specialized subject. We all know that. And it has a very wide application in India. I think since 1955 onwards, we are using pre-stressing. And though many of the designers or participants here will are aware about method of pre-stress design, but I can tell you with my experience that very few designers are well aware about the method of pre-stress design very well, the intricacies of the pre-stressing system, its technology, and the art and science of the subject. I think very few people go little deep into it, and therefore these kind of webinars are really very, very enriching. Uh, and I thank Mr. Vinay Gupta for agreeing to share his deep knowledge on the subject. And I can tell you, when I go to many of the bridge sites where pre-stressing goes on, even now, after so many years of experience in India of pre-stressing, I find that either the pre-stressing has not been done properly, or the pre-stressing which is done is not interpreted correctly, and the problem continues. So there is considerable amount of knowledge gap between what should be done and what is done, what is the practice. And there are several quality issues related to pre-stressing which needs a greater understanding, for the designers. And today is the opportunity for many of the participants. Feel free to ask questions after the presentation. And before I really hand over to Dr. Subarao, let me just introduce him. He is the chairman and managing director of Consumer Consultancy, a very well-known, reputed consultant in India. He holds a PhD from Imperial College London. He is a GC member of IS Tracti and a vice president also of International Association of Bridge and Structural Engineers, Zurich. He is a member of the technical committee of YAPSE Zurich, chair of the bulletin of editorial board. He is member of FIB Commission on Durability and Service Life Design. He is member of Highway Research Board of India and serves on several committees of IRC, BIS, and various international national bodies. He has over 30 years of experience and a number of papers and bridge projects to his credit. With this brief introduction, I can continue speaking about Dr. Subarao, but he is pretty well known to the participants. So without wasting, I would rather give the floor to Mr. Vinay Gupta and Dr. Subarao to take it forward. Over to you, Dr. Subarao.
Thank you, Alok, and for all of you all who are just listening to our president of the IS Tracti, Alok Bhaumik, welcome. That he has given you all. He forgets to mention that he is our president, you see. So that is one point I want to just put across to you. He has been very active in promoting this knowledge sharing amongst all the various fraternity that we have in buildings, in bridges, and across all domains actually of structural engineering and civil engineering. So it's with pleasure that I'm asked to moderate a session by him. And I feel very happy to be amongst our domain experts. On the one hand, I have the speaker today, Mr. Vinay Gupta, and on the other hand, I have Mr. panelist, Mr. Alok Bhaumik, and me in the middle. All of us are sort of bridge wallas, if you like to put it that way, all involved. We eat, sleep, dream about bridges all our life. So it is that kind of expertise that we want to share with you today. I would like to say some few words about this wonderment of pre-stressing, as I call it, this wonder material that we've invented. It's not very old. In 1929, Eugene Fesnay gave it its modern form and invented so-called this modern concept of pre-stressing. And up to about 1980 was when we first got high-performance concrete into being. It didn't exist till then. What was concrete? Concrete was only an invention of 4 years past 1900, 1904. So in 1904, concrete came into being in a design code in the Swiss Institute of Architects. Then in 1906, the École in Paris, they had their design code for RCC. Already by about 29 to 30, we were using pre-stressing in giving the RCC additional capabilities of durability, strength, and so many other features which Vinay will talk to you about today. And thereafter, in the history of this whole thing, along comes Magnell, who took Eugene's work, Eugene Fresnay's work. Eugene Fresnay was the father of pre-stressing, but he was a useless teacher. I mean, he couldn't get across his ideas. It was all in his head. But Magnell was an excellent communicator. And he and Guyon took this to a great dimension and made this art of pre-stressing largely available to us as we know today through their books. In fact, Magnell wrote the first book and so on. And Guyon wrote another wonderful book. And it wasn't until about the 60s, late 60s, that the German-French engineer, Ulrich Finsterwalder, then Ulrich Finsterwalder, he developed this balanced cantilever form of construction, which made large crossings easily doable, heretofore, which were always the domain of very large span cable stayed bridges or large span structures. We could break them up into sort of these balanced cantilever type constructions, isostatic structure. He was the inventor of that type. And that could only happen, those large spans could only have happened because of pre-stressing. And by about that time, we got the low relaxation pre-stress cable, which changed the way we think about pre-stressing, and it gave us huge capabilities and potential. Then Finsterwalder used pre-stressing even further. He went into the domain of suspension bridges, and he used cables to span very large lengths. And he invented what we now call the stress ribbon bridge, which is a very unique type of bridge which uses pre-stressing for spanning large gaps. So, this is the little story that I wanted to share with you. And with this wonder material, you drive along your car, you wouldn't even know you're driving on that flyover in Delhi or Bombay. It's below you. What holds it up is the pre-stressing. If you see, drive across Worli Bandra Link, all the approaches, all those structures, like I drove today from my office back home, it's all because of pre-stressing. It would not have been possible otherwise. So what is this wonder material? What is the beauty of it? What are its problems? And what is the progress that we have made? And how it is used, where it is used, and do's and don'ts is what Vinay will lead us through today. So that's the background I want to share with you. And introducing a dear colleague, Vinay Gupta. As you can always see, he is the director and CEO of Tandon Consultants Private Limited. Professor Mahesh Tandon is a mentor to many of us, and he's done so much for bridge engineering in this country that Vinay is happy to have had a mentor like him, as we also admire and respect Professor Mahesh Tandon in the bridge fraternity. So he's a civil engineer from BITS Pilani, 83 batch. He specializes in bridges, flyovers, 275-meter tall chimneys, and various types of metro structures. He's on so many committees of Bureau of Indian Standards and IRC. His contributions, including the segmental bridges, IRC SP65 guideline, the SP71 guideline on precast pre-station bridges, apart from his involvement in so many documents that are ongoing and in the past by IRC and BIS. He's also the president of the Indian Concrete Institute, which has 13,000 members all over India. And he's, of course, the president of IIBE. So he's vice president of the Asian Concrete Federation, which is a pan-Asian federation of various players and institutions involved with concrete in this part of Asia. He has got many awards, including the SB Joshi Award in 2019, so many awards from various other institutions. He's been a guest faculty at Indian Institute of Highway Engineers, in Central Road Research Institute, in the CIDC, which is one of our apex bodies for construction in India, ASDA, DPC, etc. And he's presented more than 100 technical papers. But more and above, I want to tell you that he has a very deep understanding of pre-stressed bridges, flyovers, and all kinds of buildings, etc. in pre-stressed concrete. So with that, it's my pleasure to ask Vinay to take the floor and deliver his wonderful lecture. I promise you it will be a wonderful one. I know him to be an excellent speaker. Vinay, floor is yours.
Thank you, Dr. Harshavardhan Subbarao. Friends, I must tell you, although Dr. Subbarao has said so many things about me, I don't know right or wrong, whatever it is, but Dr. Harshavardhan Subbarao himself to me is a very nice, sweet, and a perfect gentleman friend. And of course, I'm very thankful to IES Trukti for giving me this opportunity to present something which I presented in IIBE about, I think, a week or two ago. I think 2 weeks ago, perhaps. So my special thanks to IES Trukti. of course, under the aegis of the President, Mr. Alok Bhamik, no doubt. Friends, whatever my presentation today is more like a very elementary level stuff, which means that I don't expect very learned and senior people to gain much out of it. But it's really more for, say, students, or say those who exercise computers so much that they have forgotten what the reality inside is. And I am probably, our office engineers are also some of those who just click numbers, numbers, and numbers on the computer. They get some results and they think computer knows more than them. We want to know more than the computer. So that's the purpose of this today's presentation. Let me minimize my photo picture and all that. Yes. All right. So I think Dr. Harshavardhan already mentioned about these two documents, SP65, which is for the precast segmental bridges, or other any segmental bridges, precast or cast in situ. The other one he also mentioned about pre-tension girders. So we will see all these things like what is pre-tension, what is precast, what is epoxy jointed, what is dry jointed, and how pre-stressing is different for each of these items, what is bonded pre-stressing, what is unbonded pre-stressing, so on and so forth. Okay, so let me see how it works, right? And let me put it to pointer option laser. Okay. Okay, so very simple question. Why pre-stressing? Why couldn't be done with just the reinforced concrete or something like that? When you provide pre-stressing in the case of larger spans, it becomes economical because the material consumption is less, therefore the self-weight is less, and the overall economics when you see of material and everything, dimensions, etc., you will find that it can take larger loads for a larger span more easily in pre-stressed concrete than in reinforced concrete. It is faster to construct compared to RCC simply because in the case of RCC, you have to hold the, especially when it's a cast in situ structure, you have to hold the shuttering, scaffolding and all for 15 days to 21 days, 2 to 3 weeks as per the codal requirements. Whereas in the case of pre-stressing, once the concrete has gained sufficient strength, not the time, the strength of 4 or 5 days, then you get about 80% strength in the range of about 35 MP or 40 MP or 32 MP perhaps. You can decenter it after pre-stressing, which means you can do it much faster. Section size is smaller, as I just now mentioned. Now, once you reduce the concrete quantity, you reduce the quantity of cement. And manufacturing of cement, for every ton of cement, you require about, you produce about 1 ton of carbon dioxide. So once you reduce cement, you reduce carbon dioxide, you reduce carbon footprint over the earth, the planet. When you pre-stress a concrete, you act kind of against the applied loadings. And since you do that, your deflections of the concrete, of the structure, are reduced. In the process, since you are applying the compressive force into the concrete, which leads to reduction in the cracking. I would not say zero cracking because nowadays we are permitting partial pre-stressing, which will be cracked also. But with the reduced cracking, the durability increases because the passage for the water to ingress, or the carbon monoxide and carbon dioxide to ingress, reduces. So it becomes a more durable concrete. I just picked up an example that we did about 30 years ago.
Yeah.
It's a 25-story 4-star hotel building in Bangkok, Amari Atrium. You can still go now to Sukhumvit Road and see. The floors which you see from here to here are 20 typical floors with a dimension of 100 meters like this, 20 meters across the plane of this screen, and of course 20 floors. Now these things, how they have been constructed at a sea. The structure comprises, in Bangkok, of course, seismic zone is close to nil. The grids of the columns are 8.2 meters like this, longitudinally. Length of 100 meters is from here to the other end. We have these columns which are just 2 over the width of 20 meters. And these columns are 1.1 meter by, if I remember correctly, 700 millimeters. Over these columns, we have a pre-stressed banded system. In the banded system, we have beams type of things, which are 40 centimeters in this case, in one direction. And we have these slabs which are spanning 8.2 meters. That is from this column grid to this column grid, 200 mm thick. So 40 centimeters deep, 20 centimeter slab. And this entire floor was constructed, each floor rather, in 7 to 9 days, 30 years ago. Today, if you can, and of course, these bands, I must tell you that they have pre-stressing longitude transversely, and these slabs have pre-stressing in the other direction, that is longitudinal to the building. But with this whole process, the speed was as high as completing 20 floors in a matter of 6 months, 100 meters by 20 meters. Now look at the gain. The quantity are minimum because 40 centimeters depth for a span of 12 meters here, 4 meters cantilever is about the minimum one can think of. 20 centimeter of slab for a span of 8.2 meters, which would normally be about 2.5 to 3 times of it, is also about the minimum you can think of. Therefore, the quantities, all those advantages, and you finally reduce the greenhouse effect on the earth. That's what people talk about nowadays, greenhouse effect. So those are the advantages. Now for a hotel building, if you saved the entrepreneur about 3 weeks or 4 weeks for every floor, and therefore he starts his guest entry and all that 1 year before or 2 years before, his gains are enormous. What is the cost of a structure? Structure being cheaper, faster, and yet economical, and for the entrepreneur to start earning his buck faster. So those are the advantages, distinct advantages, I must say. Okay, so we have seen normally the round pre-stress where you have a round duct, round anchorage cone, round everything. But for the slabs where you have only 4 or 5 strands and thin slab, like in this case 200 mm, this kind of flat ducts are available wherein you put these 4 or 5 strands depending on the design, and at every some spacing, which can be a meter, half a meter kind of a spacing, and you provide a pre-stressing. You may notice that in the slab, one side is dead end anchor, other side, and this one will have the anchorage end on the other side, and this one has pre-stressing end on this side, dead end and anchor on the other side, so that we have a symmetry of forces as far as possible. This is a pre-stressed concrete, rather post-tension concrete truss for a large factory building constructed in late 1980, 1989, 1990 types, about 30 years ago again, where the concrete trusses which we see, all this, they have these bracings, the top boom, the bottom boom. The bottom boom, which is into tension, is pre-stressed. Just by this pre-stressing, the whole thing has become very fast, very light for a span of 25 meters. This depth is about 2.2 or 2.3 meters, I don't remember. And these are 10-meter tall columns. And the spacing of these trusses is about 10 meters. So again, for a factory building, which was for a color pictured tube factory, that fat TVs of the old times, for manufacturing of those, and they wanted to beat the competitors. And when the factory was constructed in a matter of 11 months for 25,000 square meter 30 years ago, they really were applauding. Okay, so we talk of pre-stressing now. Back to, to basics of pre-stressing. In pre-stressing, we have 2 categories: pre-tensioning, where you tension the tendons first and concrete later. We have post-tensioning, where you concrete first and then tension the tendons. Tendons, when I say tendon is pre-stressing, it can be a strand or it can be a cable. But tendon is a common word, whether it's in pre-tensioning where we have strands or it is post-tensioning where we have a cable. We'll discuss this also. In pre-tensioning, since we do these strands, put the strands first and then pour the concrete, it can only be bonded. There's no question of unbonded pre-stress. In the case of post-tensioning, there is internal post-tensioning, there is external post-tensioning. Internal means the tendons are inside the concrete, which is a normal case as you see. In external, the tendons are outside the concrete. They may be, like in the case of eye girders, they can be outside the concrete girder. If it's a box girder, they can be in the hollow space of the box. But in both the cases, in external case, the tendons are not into the concrete, they are outside. Now in external, you only have one category, that is unbonded, because the pre-stressing is not bonded to the concrete, it is outside the concrete, so it's unbonded. In the case of internal, you can have bonded, which is normal, what you normally have in your concrete, but you can also have unbonded tendons with the help of something which can permit sliding of the strands of the cables. Means you can have a grease or a wax grout instead of cement grout. So that becomes an unbonded cable. In fact, the hotel building that we saw just now, there we have used wax coated strands in individual HDP tubes. So they are actually unbonded internal pre-stressing, that is this category: pre-stressing, post-tensioning, internal, unbonded. But we'll discuss each of these in detail. So let's talk about the first two family members, that is pre-tensioning and post-tensioning, before we go to their further downward family. In post-tensioning, while concreting, we place a duct or sheathing in any profile that we want in the positions at the levels where the tension would occur. Like in a simply supported span, you'll have tensions at the middle, more here and less there. So we put the pre-stressing cable in the same way to impart a compression. And thereafter, after concrete having gained the strength, requisite strength, we thread the cables and we stress the cables. So we impart. And once we impart, this structure tends to lift up because there's a reverse force. Loadings are not as much, and therefore this tends to lift up and free the shutter below if it's cast in situ. In the case of pre-tensioning, we first take the strands and pull them straight with the help of some jacks with some supports. Once we have pulled the strands, now we pour the concrete, and concrete of course comes around the strand, so it gets bonded. And once the concrete gains requisite minimum strength, we release the jacks on either side so that the force in the strand or elongation of the strand can be transferred to the concrete. And now it compresses the concrete. But since in normal case, I would say, of course there are other examples, but since we are stressing the strands first, they will be essentially straight from one end to the other and not curved like this. Though this is a better profile, but this entails more concrete dimension, larger concrete dimensions, more quantities in general. It is cheaper where you have lesser numbers of girders. This one is cheaper where you have larger number of girders, say 200 plus, because the initial cost of setup for this is high. But nowadays, very commonly pre-tensioning is being used. Of course, one question may arise that then all this is straight and the bending moment is lesser here. Will this section not get over pre-stressed? So let me answer it right now before anybody asks. What do we do is part of the strands, some of the strands, we debond them here. How we debond is we provide a HDP tube around the strand, individual strands, so that the concrete does not come in contact with the strand for some length. So part of the strand lengths get debonded so that our stress control does not fail. We don't get tensions at the top and cracking at the top. Just to remind you, if I'm not wrong, if the organizers also agree, your questions must come in the question answer box.
That's right. That's
Okay.
right, Vinay.
So please follow this. Yeah. And please place as many questions as you like. I'll be very happy answering or learning from you.
And mute everyone, please mute except the speaker.
All right. So now we just talked about post-tensioning. So in post-tensioning, we have a cable. What a cable is, we will see. And around the cable, we have a duct, which can be metallic or high-density polyethylene, HDPE. And in this space, we normally provide some grout or the other. If it's a bonded pre-stress, then we provide cement grout, so that from the cable, we have cement here attached. From the cement, we have the duct, and from the duct, we have the concrete. So everything becomes one bonded stuff. If we want an internal unbonded pre-stress, in unbonded pre-stress, we provide a flexible material here like wax or grease. a selected quality wax and grease, which have good life, 100 years and all that. So once you put that kind of a material, then the bonding between pre-stress and the duct does not take place. Only protection takes place against weathering, because pre-stressing can get corroded very fast or faster than regular steel due to high stress. In the case of pre-tensioning, we don't have a cable concept. We have a strand concept. Each strand is placed in its place wherever we have decided to. And after the strand is stressed, we pour the concrete. And of course, reinforcement is always there and already there. And once the concrete gains sufficient strength, we release the jacks for the pre-stressing force on the strands to be transferred to the concrete. You may notice a word. Tendon is a common word. Tendon may be either in the form of a cable that's like this, a grouped cable, or it may be in the form of a strand, which is like this. So the international books, literatures, and codes, they more use this term tendon as opposed to a strand or a cable, because it's a common family of pre-stressing. All right, so let us see what a cable is and what the other things are. What you see here is a strand. This one is a strand, but this whole thing is a cable. What is a strand? Let us see. A strand comprises 7 wires. One is a central wire that we see here, and there are 6 outer wires. Stranded together in the factory, they make a strand which is 7-wire strand, and in these strands, the central wire is 1.5% larger in diameter than the outer 6 wires, and that becomes a twisted strand. We really feed 7 coils in the factory, 1 central coil, 6 outer coils, and the strand and the wires are pulled from these coils, and there's a rotor which rotates. So as the wires are drawn, the rotor rotates, and that creates a stranding of the 7-wire strand. So that's a strand. Now, when you say 12T13, a very common one, 13 means it's actually 12.7, which is ½ inch, which is a nominal diameter of each strand. Nominal means this nominal diameter. It is not a solid diameter. It is less than the area of a solid diameter, but a nominal diameter that you get, a round diameter, is 12.7. So that's a strand. When we have 12 such strands, each one is like this, and there are 12 such, this becomes 12T13 or 12T, some people call it ½ inch also. So that is how this strand is designated. Or when you say 19K15 or 19T15, whatever you call it, there are 19 such numbers, and each one has a nominal diameter of 15.2 millimeters. It is also called 0.6 inches. So that's how the terminology goes. I think more commonly nowadays we are using 15 mm strands. Okay, now these strands which are into a duct, which can be metallic or HDPE, that lives inside the concrete. And at the end of the duct, we have a conical anchor head, which is what you see in the lower picture like this. So this part, all this part remains inside the concrete. There's something called bearing plate, which is here. This comes outside the concrete, and this is placed after the concrete has hardened. All these things which you see here are placed beforehand, and concrete is concreted. And it's of course, we are talking of the internal pre-stress, and we are mostly talking of internal grouted bonded pre-stress. So this one is that because that is most common in our country and even anywhere else, I would say. Now, in the bearing plate, we have conical holes. Each of these holes that you see here are conical. In the conical holes, we place these wedges. Wedges means they're also conical in shape, and inside surface of the wedge has serrations like as if like teeth you have in the nut and bolt. Those kinds of serrations they have inside the wedges, and these wedges themselves are in number of pieces. Some manufacturers have 3-piece wedge, some manufacturers have 4-piece wedge. These wedges have a very hard internal surface, what you call it as serrations, and these serrations bite the strand. So what happens now? You have the strands lying here, all these whole cable strands, These strands are about a meter longer or so to be engaged in the pre-stressing jack, which is hydraulically operated. Now these strands are pulled. When you apply a stress, a strand is a metal is elastic, and any elastic material pulls. So it pulls. It's something like 7 millimeter per meter length is a normal pull of a strand. So a strand comes out in the jack. Once the strand has come out and these wedges are there, you slightly hammer them lightly. Lightly once you hammer and now release the jack, the strand wants to go inside. So it's under a very high stress. But these wedges, since they're conical, they start biting. And due to the biting, the strands cannot move inside. And therefore, the stress remains onto the concrete, the compressive stress. Interestingly, when this process takes place, that is when the strand goes inside and the wedges try to prevent it from going inside, some slippage of the strand does take place here in the range of 3 to 6 millimeters, and we call it wedge draw in. Wedge draw in, wedge moves before it is able to completely grip the strand and prevent it fully from moving inward. And with this process, the force gets reduced a little bit, no doubt, but at the same time, the force gets locked onto the concrete structure. So these are those wedges, 3, 4 pieces, whatever there are. This is the entire thing. This is just a cut cross section only to demonstrate. And there's always a question, what should be the internal diameter of this duct? So these are the stipulations, but more detailed stipulations are there in IRC 112 as to what should be the internal diameter, ID, of the duct for each size of cable. Right, this is the one that we discussed for the building application, but when you have a transverse pre-stressing in a box girder or something, or even transverse pre-stressing in the case of spine wing structure, which I'm sure of a precedent has designed several, and we have also designed a few, and we have proof checked a few. So in those cases, the slab, which is about 220 millimeters or 250 millimeters or so, our pre-stressing is of normally this type, with 4 to 5 strands in the pre-stressing, flat ducts, and a flat kind of a anchorage cone assembly. Rest of the things are the same as other cable. These are pre-stressing ducts. Either they can be metallic. Metallic means it's made out of cold forming process of metallic sheets. Metallic strips are cold formed like that and interlocked. Whereas in the case of high density polyethylene, that is HDPE, it's just a SDP extruded material in the factory. And each piece of this HDPE duct is in the range of 6 to 10 meters length. So each piece that you get is 6 to 10 meters. And after every 6 to 10 meters, you have to have some method by which you can couple the two. Best form is a coupler like this, and along with the heat shrink tape here so that it's slurry tight. It has to be slurry tight. No slurry should go into the duct. Or it can be any other system that works efficiently to ensure that the cement slurry, which is in the concrete, does not go and block the duct, which has happened in many, many cases. You see something here? Maybe you notice it later on. These are the pipes which are connected to the ducts for grouting. What we talked of grouting. Normally I'm talking of cement grout, but there can be other materials. So for grouting, we provide these kinds of pipes, grout pipes, right in the beginning. Okay, when you have to continue the pre-stressing for long continuous bridges, then we can also provide couplers. In the coupler, supposing our first set of concrete is still here, and later on this concrete will be poured. So what we do is that we have a coupler placed in the concrete. It's a fixed kind of coupler, as we call it. In this, you have 2 layers, circumferentially 2 layers of pre-stressing strands. The outer layer that you see is stressed from the outside first. I mean, assuming that the left side concrete is first poured. So jack is placed on the right side to pre-stress the outer layer of strands, wherein these strands which you see inside, the inner layer of strands, they are placed and they are projecting out but not stressed. And this will be a dead end for the next cable, for the outer, this cable. And from the other side, on the right hand side, there will be another end where we pre-stress. So this way we can have long continuous cables made in stages. because normally strand length can be anything, there's no problem. A strand can be 3 kilometers long also, and strands are as long. But thing is that we cannot be constructing all of it in one go. We have construction going on in stages longitudinally. So we can have a coupler like this, but this coupler is quite expensive, keep in mind, as a practical engineer. So the other thing that is more commonly used nowadays is to provide a pre-stressing and overlap the pre-stressing like you would do for the reinforcement, very much the same way. All right, so now let us see the same pre-stressing, the family, which is post-tensioning external and unbonded only, because these are something which is not so common. So let us discuss external, and it can only be unbonded. Let us discuss that also. This is, of course, a project that we did, and also I think our president, IES Trustee, Mr. Alok Bhamik, also did parts of this project. He also did. Metro in Malaysia in 1995, where we have used this external pre-stressing, which means that pre-stressing is inside the hollow space of the box girder. These are the end diaphragms. There are some deviator blocks which are in concrete, so that the pre-stressing cable can go into the block for a deviation of angle. Because you need this deviation, your bending moments are more here, they are less here, therefore tensions are more here, less there, and therefore the cable has to run in this profile as far as possible. But it is not into the concrete, it is in the hollow space of the box that looks something like this. So we have a lot of these cables with SDP duct. SDP is more or less inert, whereas metallic duct or metallic sheathing is not inert, and therefore in the external application, metallic sheathing is not permitted at all. It is only SDP, and in the case of external, the requirements of SDP duct wall thickness are little more than that for the internal one, because they are all by themselves, and they have to also negotiate this deviator block. As you see, the cables are going down and then running straight and then going up somewhere. So that's how the external pre-stressing works in the case of, and where it anchors, there are diaphragm. In the diaphragm, you have an anchorage, cone, and the pre-stressing would come here and get anchored here. Somebody may ask me, why use external pre-stressing at all? External pre-stressing has an advantage that this can be replaced more easily. So in our codes also, we have permitted external pre-stressing so that you have the distinct advantage of replacement. As I see, that is the only major advantage. But one more advantage that we saw in Malaysia was that with the external pre-stressing, the speed of construction is higher. And that is because, as you may notice here, or I may tell you here, that at this joint of precast segment, there is no epoxy application. So you save the time and cost of epoxy application. These are dry jointed segments. And you don't have to apply a temporary pre-stress across the epoxy. So you save that cost, time, everything. Why? Because this pre-stressing cable does not require a weathering protection from your concrete. It is not in the concrete at all. It is outside the concrete. So it's a continuous SDP duct. It has its own grout inside. It doesn't require any protection, and therefore there's no risk of these joints of the segments leaking and causing any kind of a problem to the pre-stressing which is inside. Instead, they can be dry jointed. Of course, due to some other analytical, or I would say for performance reasons, the dry jointed segments are reducing worldwide. Some of the codes don't even permit it now. But yes, people have used a lot of it, especially in eastern part of the world. Okay, come to pre-tensioning. The next very common type of pre-stressing in India is pre-tensioning. So let's discuss this. Of course, you have IRC SP 71 with you. Now, most of these metro structures which you see with the help of this form of U-girder, they're more or less all of them pre-tensioned. Typically about 25 meters span, typically about 5 meters wide, means this is 5 meters, 25 meters span, pre-tensioned in the factory, and after pre-tensioning brought to the site. And this is a pier cap. In general, mostly it is transversely pre-stressed, and you have a RCC pier. So this is a project that we have done from Noida to Greater Noida, where 30 kilometers was constructed by more or less the same technique, wherein even the pier caps are precast post-tension. Okay, talk of this Bangalore metro. If some of you are from Bangalore, but of course in any city nowadays, these girders at the concourse level, the place where you go and pay your tickets, etc., or these girders which are at the platform level where you alight aboard the train, are all precast, pre-tensioned eye girders in this case. We have found that whenever the number of girders exceed about 200, pre-tension becomes economical in terms of cost. Time-wise, it is always faster than post-tension girders. So we go for pre-tensioning for these cases, but we will see what it entails in pre-tensioning. Of course, this is one more project, which is a Delhi-Gurgaon Expressway, 26 kilometers long totally, and about half of it is using these flyovers, long flyovers, as long as 2 kilometers and all that, which are using precast, pre-tensioned girders of 25 to 30 meter span and continuous, made continuous. Okay, so since this is a common technique, so I thought I will show this here before we go into other types of aspects. Okay, what is done here is, as I told you, that we have to first stress the strands and then pour concrete. So what we do is, we have one bed which is here, which can take 3 girders of 30 meters in this particular case of Delhi-Gurgaon Expressway. We have another bed of 3 into 30, and we have 2 other beds of 4 into 25 meter girder here. So totally we have 14 beds available in this particular project. I'm taking a practical example. Whole thing is made long line, wherein the reinforcement is tied here. There's a crane that moves, Goliath crane, supported here and supported here. It can move all the way from left to right and right to left. It will pick up the reinforcement, drop it into the shutter. Not drop it, rather drop them one after the other. There are 4 such, 3 such, 3 such, and 4 such. So each of these 25 to 30 meter long the reinforcement, which will be assembled and tied here, will be taken and dropped here. This side we have dead end, and this side we have a live end of the pre-stressing end. Same way for the other side, we have live or pre-stressing end and dead end here. Same thing happens here, same thing happens there. We have jacking assemblies. No, it's not just a jack, it's jacking assemblies. That's a difference. So we have a jacking assembly here. These are the 2 jacks in this case. Each of the jack has a capacity of 500 tons. And it can have an elongation of 600 millimeters. Why 600 mm? Because 6 to 7 millimeters is the stretch of a strand at its stress that we provide per meter, 6 to 7 millimeters. So we have a length which is approximately 100 meter, and therefore the jack has to elongate 600 mm. That's a calculated value. Same way 2 jacks, and what is here is called movable trolley. So what we do, the strands from here are engaged in the movable trolley, which is a metallic trolley, heavy trolley. And these jacks, they push the trolley backward. So these jacks, they push the trolley backward like this. So when they push it backward, in the process, the strands which are anchored here, they get pulled like this. Simple process. And of course, there's a batching plant. There's also a steam curing plant in this case that we used. And with this, we got a speed of 3 days per bed as a construction speed. So look at the shuttering here, because here speed is important, and they were producing up to 105 girders per month from these 14 beds. So here, as you notice, there's a single piece shutter for 1 girder, another one single piece for 1 girder, which can slide in and out quite easily with the help of jacks. And these are the movable trolleys. By putting the jacks here, which you don't see, of course, they can be moved backward. I'll show it to you. This is a closer picture of those shutters, which can slide inside the bottom. Bottom is raised so that this shutter can move in and out quickly. These are those jacks. So these jacks will do the job of pushing the trolley backward. Once the trolley is pushed backward, these strands are pulled this way. This is a stressing end. This side is a girder. On the left side is a girder, which is to be cast. So here the strands In this case, they were in the range of 40 number of strands. They are pulled, and once the strands are pulled, you pour the concrete here into the shutter, everything, and the job is done. And of course, once the concrete gains sufficient strength, you can release the jack from here. The trolley becomes free. The strands get inside, get into the concrete, and there are no wedges, no duct, no grouting in pre-tensioning. And therefore, the concrete dimension is smaller. Cost of grout is gone. Cost of duct is gone. Cost of anchorages is gone, because the anchorages are only engaged into the trolley. This acts like a pre-stressed reinforcement. It just sits in the concrete with the stress. This is the dead end. Let me keep checking the time. Okay. So this is just one more picture showing the shutter and the, what do you call it, reinforcement. This is just the end of the girder. Now, since at the end of the girder, we'll be connecting a cast in situ diaphragm, it is important to have the shear strength in a proper way. That is the connection, the construction joint between these precast girders and the diaphragm at the end. And let me tell you that this entire project with Delhi Gurgaon that I'm discussing with so much of passion was completely proof checked by Dr. Harshavardhan Subbarao and his company and his father, Dr. T.N. Subbarao. My thanks to this team that they suggested, apart from all of the suggestions, how to really do the 100% hacking of these precast girders. This is manually hacked with a chisel, 100% in such a way that every aggregate is visible. Otherwise, you may find that in some of the projects, some of the structures, there are cracks that are visible here, and nobody likes to see cracks. It's always a weakness. We also do splice girder, which means we make several pieces of precast pre-tension girders and then pour this wet joint for long one. Like in the case of it's 45 meter long, and each one is about 9 meter long precast pre-tension girder. And we, after pouring this wet joint, that's a concrete joint, then we put a post-tension pre-stressing cable and stress. Just a casting picture. All right. So let's take the next one. That is post-tension, internal, unbonded, which is not common, I must say. And I don't think there's any structure in India. Of course, it is there. I would like to hear from the panelists and other people here. A structure which is internal, pre-stressed, but unbonded. Of course, I have showed you one, that is the Bangkok hotel, unbonded. So what we do here is, this being the strand, this being individual HDP duct. Between the two, we provide a grease, a coating of grease or wax. So protection of the strand comes from the coating, but it also permits a movement between the HDP tube and the strand because we have a flexible material. And of course, this HDP tube gets bonded to the concrete around, but between the strand and the concrete, there's no bonding. So the big difference of design is that the strains in the concrete are not the same as the strains in the steel at every point. Unlike what you see, the first assumption in your RCC designs, IS 456, it is presumed that the strain in the concrete and the steel would be the same everywhere. It is fine for the bonded pre-stress, but not definitely fine for unbonded pre-stress. So that is one difference, but advantage. Again, somebody will ask, as a practical engineer, what is my benefit of doing this? It is costlier because compared to cement grout, wax and grease are more expensive, much more expensive. Advantage is that these strands, in case they get corroded or something happens, you can remove the strand, put the new ones. Very much similar to external pre-stressing. Here, unbonded pre-stressing, you can remove the pre-stress and put the new pre-stress. So you can do a replacement therapy. And of course, there's another picture where you can have one more protection, that is epoxy coating of the strands. And after that, put them into the SDP tubes. And SDP tube up to the strand, you'll have a grease or wax. But between this SDP tube and the bigger SDP tube encompassing all the strands, you can have a cement grout. Even then you can remove the strand because there is a SDP, there is a wax or grease here. All right. So there can be various levels of multi-level protections, we can call it. I think I'll skip this for the moment. Let's go to next topic, that is epoxy jointed internal bonded, the regular one, regular internal bonded. This is the most common pre-stressing. I've taken it at the end because I know this is well known to most people. But of course, we'll take segmental, that means precast segmental and cast in situ segmental. Now, what is segmental? Segmental is something that you do in stages. For example, if you do a cantilever construction and if it is in situ, it's a segmental but in situ. Or it can be a precast segmental that you see very commonly for metro and many other structures. This way, like for example, this is precast segmental. And in this particular case, this being Barapula elevated expressway, in fact, proof checked by Dr. T.N. Subbarao and Dr. Harshavardhan Subbarao, the father and son company, customer consultancy, way back in 2008, 9, 10, Commonwealth Games 2010. So these precast segments are arranged together and post-tensioning is done. In the case of precast segmental or even in situ segmental, your pre-stressing will normally be, or rather only be, post-tensioning. So there's no question of pre-tensioning. You cannot put the cables first and the strands first and then you start concreting. So it's always post-tension. This is another structure. If somebody is from Bangalore, is from Silk Board Junction to Electronic City, wherein overhead launching truss was used, launching girder, and these precast segmental structures were constructed 10-kilometer long, various stages of the construction, which is not the forte to discuss right now. But when you use segmental, epoxy jointed, internal pre-stress, you have to apply epoxy on these surfaces. Epoxy means resin and hardener combination, which is like araldite, between the segments. For applying that, segments have to be lowered to create a space. After creating the space, you apply epoxy on the surface, and then you bring the segment up and you do a temporary pre-stressing between adjoining segments for 24 hours so that the pre-stressing or other epoxy gains the strength in 24 hours, which is just adequate for the proper glue to come effective. Glue means we call it glue, epoxy glue or whatever. Okay, I'll skip this. Okay. So this is the epoxy application. Here, by Hessian cloth or something, they're using this 2-component epoxy mixed together with a high RPM rotor mixed together, colloidal mix, and then they're applying the epoxy on the surface. Now this epoxy, be very careful, it must be thoroughly made available from this end to the other end of the surface. In many projects we have seen that some people have not been careful about it, either due to cost reasons or something, and therefore the epoxy is not available. At the same time, also be very careful that the pre-stressing ducts, they will have joints at every segment location, which is maybe 2 meters, 3 meters, or 4 meters. The chances of ingress of this epoxy into this space are quite high. And if this goes inside, which has happened in some cases, the pre-stressing cable cannot be threaded. And if it can't be threaded, you don't know what to do. So this kind of a neoprene ring or neoprene washer is provided around each of such joints. We should not save on this, we should provide it religiously. Apart from that, we will also talk of duct couplers at these junctions, which we are bringing into the code also now, so as to make the duct fully properly continuous at the joint, at the precast segment joint, and also at the same time with this kind of a thing so that the epoxy material does not get inside the duct. These are those duct couplers. We have precast segment here, precast segment there. It's coming in the code now. We have a female coupler here, another female coupler here, and we have a ring which can go into both the sides of it, small ring, when the two segments come close to each other so that the duct becomes sort of continuous. Sort of. This coupler, of course, is another thing that we do for regular continuation of the coupler, the duct. Now, if you remember this SDP duct, the available lengths are only 6 to 10 meters. They are not in 100 meter of 80 meter, 50 meter. So they have to have this kind of jointing every now and then. So the jointing has to be very effective so that no cement slurry gets into it. I just picked up two pictures of one project, which is another kind of precast segmental, where transversely also it is precast in segments and longitudinally anyway precast segmental. So transversely we have a spine which is precast segmental longitudinally. We have these wings which are attached. It's a spine wing construction is called. It's becoming very common nowadays. In fact, the IAS structure president, Mr. Alok Bhaumik, has already designed few of these, as I discussed, as I said some time back. And you put transverse pre-stressing also in this case, because transversely also it is into 3 segments. So you require a pre-stress. This is a wet joint here. So I thought I'll just show it. It was first time done in India, in Mumbai, JJ Hospital viaduct, 2.5 kilometers long. I think Gammon did the construction, the erstwhile company of Dr. T.N. Subbarao. All right, now we discuss a simpler thing, cast in situ, segmental, internal pre-stressing, bonded, which is majorly, I would say, cantilever construction that we use very commonly. Say if you are doing a balanced cantilever construction or cantilever construction of some type, you construct about 2 to 4 meters at a time and you put pre-stressing. So when you do this every now and then, every 3 meters or whatever, you carry out a segmental construction cast in situ. This is also a segmental construction, keep in mind, and this SP65 does cover this as well. Now here again, you have to worry about the continuation of the ducts for taking the pre-stress cable, because the ducts are going to be jointed one after the other very frequently. So that's important. In this, of course, construction is that we have a traveling formwork. There's a truss on top, which is connected to the superstructure here and also here. It takes and it's a cantilever which supports all this weight of the shutter, concrete, everything. And every time it exerts a downward load and a tension here anchored to the deck, of course. And you cast this, you pre-stress it from this end to the other end. You go on for the next segment. That means you move the traveler to left side, this traveler to the right side, cast the next one, and go on and on and on. Likewise, you construct what you saw just now. One very important aspect of pre-stressing is grouting. Protection of a pre-stressing cable is much bigger must than that of a reinforcing bar. And this is because reinforcement is staged at a low stress of about 300 to 400 MPa, whereas the pre-stressing is staged at about something like 2 to 3 times of this level. Because the basic stress or rather 4 times of that level. Because the basic stress level is say 500 here, 1860 in pre-stress. So that already is about 3.5 times. Then when you put the pre-stressing and it undergoes some losses, even after that, it is in the range of 3 times of stress compared to reinforcing steel. And when the steel is at a higher stress level, the chances of its corrosion are more. It does corrode more. So it needs a better protection. Now, the fact is that you normally, if you talk of internal pre-stressing, post-tensioning, you provide a duct, which is something like this. Something like this means I'm assuming there's a support here. So there's a hogging bending moment here. There's another support here. So there is a sagging bending moment here. Likewise, this kind of things are there. Our codes are nowadays very clear, which was not the case about 30, 40 years ago, that you have to provide effective arrangements for grouting of these ducts. Effective arrangement means one vulnerable location where the grout may, okay, what is grout? Sorry. At this place, you have a grout tube at the anchorage cone. That grout tube comes out, which is connected to the inside of the duct in the trumpet or the anchorage cone. And in this grout tube, you're supposed to send a high pressure grout. What is grout? We will see in a while. Cement and few things. Send this grout in such a way that the grout reaches everywhere, all the way to the other end. But how to make sure that the grout has reached here? It may not be reaching everywhere. So one is you make a volume calculation to see that the complete volume that you theoretically think is necessary for it to fill up has reached. The other is that you provide at the apex points, you provide a tube to see that the grout traveled, grout reached, and grout came out. Once the grout comes out here, you're sure that grout has reached everywhere. Now close this end, let the grout flow further. Let it go down to valleys, let it go come up at the crest. And again, there will be a checking tube there wherein you check. At the same time, much before the grout, we also check that there is no blockage in the duct. For checking that, we send water, and to see that the water has reached everywhere all the way with the volume and the same thing. And thereafter, we drain out the water through the drain, so there's a drain. So all these things have become very clear in our codes nowadays. This is a grout mixer, which can create a colloidal mixture that's very important. It has to be homogeneous colloidal mix, which you have to prepare with a equipment like this. And everywhere you need this kind of grouting tubes, outlets, so on and so forth. Now, a good quality grout will be this, the most ideal one, that around every strand there's a grout. So there's a protection to all the strands with the grout, and then grout gives a bonding from grout, from pre-stressing strands to the duct and duct to concrete anyway. But what happens, a poor grout is something like this. The strand sat at the bottom, you try to send the grout reached somewhere, but grout could not reach some of the points like this. And then what happens as a result is this. Endoscopy was done for a bridge in Karnataka, and they found that the endoscopy means, you know what endoscopy is. The endoscopy camera is sent to your intestine, that's endoscopy. Was sent here into the pre-stressing duct, and the ducts were found empty in many places. And that resulted into extreme amount of corrosion of the strands. That's what we don't want. So this protection is very important, and for that there are specifications. This is, if you talk of material, there is cement, there is water, there is non-shrink additive, so that the whole thing doesn't shrink into the duct and create a separation. There are plasticizers to give you high slump so that it can travel without holidays, without breaks. There has to be a bleed control stabilizer, because the whole thing, which is only cement and some admixture, can have excessive bleeding. So to avoid the bleeding also, there is something you have to add, that's a bleed control stabilizer, like what you put also in self-compacting concrete, a bleed stabilizer or a viscosity modifying agent. It's a different kind here. And sometimes, if the specifications ask for, in the case of highly corrosive environments, corrosion inhibitors, which can again passivate the environment for preventing the corrosion further off. And of course, there are specifications, water cement ratio, limits of deleterious materials. And other thing is that in order to avoid this problem of mixing cement and this and that and all these admixtures, there are ready-made pre-packaged grouts available, which is a complete mixed powder. You just mix water and use. So they are superior, more expensive, but control is automatically better because they are factory produced. You just have to mix water and use it. They come in the packet powder. All right, so let's talk of a very important aspect, and I suppose I have 20 minutes total left over. Pre-stressing gives you a lot of advantages, but any good things come at a cost. So the cost here is that you end up wasting some more money in pre-stressing on losses in the force, but you have no choice. It's the behavior of the structure. Unless God is very merciful, sometime 20 years, 30 years down the line, that they make a concrete which is non-shrinking type or non-creeping type, we have to live with it. So the losses are wobble of the duct, that is pre-stressing the wobble. Duct may go up and down like that depending on where it is supported. So it's wobbling up and down, up and down. Friction in the duct because of the wall, type of the wall, that is metallic, SDP and so on. Or the type of coating on the pre-stressing cable itself. Sometimes it may be bare, sometimes it may be galvanized or epoxy coated and all that. Wedge drawing I discussed and I told you. The strands under the tension, constant tension, they undergo a relaxation. That means the force is reduced because they are continuously under tension. Intrinsic particles of the strands, they go some kind of a relieving, some kind of a relaxation. And that's a relaxation of strand, which is time-based. Concrete shortens, once you apply axial force, PL upon AE, the simple formula, the concrete also shortens. Once the concrete shortens, there's a loss of cable force because you elongated the cable to about 6 to 7 mm per meter, but now the concrete is shortening, the force reduces. Supposing if you take an example that you have a cable or a structure or a girder, which is 20 meters long. Over 20 meters, your elongation of the cable, left and right together, will be in the range of 160, 120, 140 millimeter. Let's take a figure of 100 mm. Now, once the elastic shortening takes place and if concrete reduces by 2 millimeter, then 100 mm, which was there originally, has become 98, so 2% losses right away there. Then shrinkage of concrete. The concrete shrinks with time anyway, that by itself it shrinks. So when the concrete shrinks, again there's a reduction in the length of the strand, and therefore you have a loss because the elongation reduces. Creep is another phenomena which is localized along more or less along the cable. Wherever the stress is more, creep is more. And of course the other factors that affect. So all these things are available in our IRC 112 in a straightforward manner, tabulated values. But in case you want more detailed calculations to be done for whatever reason, then Annexure A2 gives how to calculate these losses, taking specific effects of humidity, perimeter ratio, time, this and that in more detailed manner. Or temperature, that's another aspect. Okay, so when we stress a cable, our guiding factors are that the stress in the cable during stressing operation should not be more than 90% of the 0.1% proof stress or proof load of the cable. 0.1% is 0.85% of ultimate tensile strength. So 0.90% of that becomes 76.5%. And once you release the jack and the initial setting and all has taken place, that is elastic shortening and encourage slip, wedges, wedge drawing, and of course wobble and friction have taken place, then this shall not be greater than 75% of ultimate tensile strength FPK or 85%. What was 90 here has become 85 after those immediate losses. Okay, so I think we are quite used to computers. In the computer software, we feed a cable, we get forces, we get some profile, but we normally say, okay, computer is more intelligent than me, and therefore I trust whatever computer has given. But that should not be the approach. Let us understand. This is the line, zero force line, or jacking force line, sorry. And we stress, and the stress of the cable reaches here after stressing. That means stress has gone up. When we stress, the duct applies a reverse reaction, like a resistance. So we stress like this, the duct with its friction and wobble will apply a reverse thing to reduce our forces. So if nothing happened, then these forces with the distance will keep on reducing because more and more friction and wobble would have taken place over a longer and longer length. Now we release a jack. Once we release a jack, there's a wedge drawing. When the wedge drawing takes place, the strand tends to go inside. When the strand goes inside, it is a reverse force in the strand, which is countered by the friction and the wobble in this shape. So finally, you see that this from here to here goes up, then here to here goes down. And this loss, if you take the area of this triangle, is the one that comes from the wedge draw in, the 3 mm or 6 mm. At one time, this wedge drawing used to be 6 mm. Then they have gone on improving the wedges. And nowadays, in most cases, we take 3 millimeters, although we ask the supplier of the wedges. So we take 3 millimeters as the wedge drawing. And therefore, this loss figure has reduced over the time. But fact is that the cable force increases and reduces. You will see this phenomena in your computer software output also, if it's correct. But thing is that you must appreciate, recognize, and understand the reason for various reasons. For example, if you're making a check of the stresses, and supposing the midspan is here, okay? At midspan, your bending moment is higher if it's a simply supported span, but the pre-stressing force is low. At the same time, if it is quarter span, at quarter span, the bending moments are lesser, but the force is the highest. So you have to see that your structure is safe for that force where the pre-stressing is higher, much higher. Because in the case of pre-stressed concrete, since pre-stressing is active force, you cannot impart more. And of course, you can't impart less for the structure to be safe. If you impart more pre-stressing than required, you'll have a cracking on the other face. Okay, so losses due to friction and wobble, they are controlled by this formula that force after the losses will be initial force 1 minus E, that's a friction, and this is a wobble. So theta, whatever is the angle, and friction coefficient, and here is a wobble coefficient K, and X is a distance over which the thing is taking place. So value of mu depends on the surface characteristics of the tendon and the duct, on configuration of the tendon profile, and on the presence of rust, if any. Rust will cause increase of the losses. The value of K for wobble depends on quality of workmanship, distance between tendon supports. Keep in mind, tendons mean that the duct has to be supported very often so that the duct does not go up and down. If it does, losses will increase. In fact, the losses are only a broad estimate. Actual losses may not be the same. They may be less, they may be more. Both possibilities are there. So I'll discuss that also in a while. Now, talking of these, what do you call it, the losses of friction and wobble, let's concentrate on the second part, that is stress relieved strands that we normally have. If you have a bright metal or metallic duct, then these figures are 0.0046 and 0.25. But the moment you change it to corrugated SDP duct, it reduces to half, and here it's about 2/3. So the losses of this kind are lesser in the case of SDP ducts compared to metallic ducts. All right, so now relaxation of the pre-stressing cable. As I mentioned, you have a pre-stressing cable and you stress it. And just you hold it like this. The length of the strand remains the same, but the force goes on reducing over a period of time slightly. Slightly means something like 2.5% over 45 days, which is 1000 hours. So if you have a stress, supposing if you imagine a constant stress of 0.7 times the FPK, FPK is nothing but ultimate tensile strength, then there will be a loss to the extent of 2.5% in today's type of strands. That is total electrician. Over 1000 hours. And over infinity time, it will be another 2.5 times of it, theoretically. So you'll have 6.25 times. And within 1000 hours, if you're dealing with, let's say, precast pre-tension girders and all that, then again, for every hour, this percentage is given. After 1 hour, 37% of the 1000 hour relaxation. 47, after 20 hours, it is 57. After 500 hours, it is 900. And after 1000 hours, it is 100. So the loss is more in the beginning, less later on. All right. Now we talk of another loss, which is also a time-dependent loss. Now let's recollect. Wobble, friction, wedge drawing, and elastic shortening of the concrete. They are one-time losses. They don't go on with time. But relaxation loss is time-dependent. Shrinkage loss is time-dependent. Creep loss is also time-dependent. It goes on with the time. More in the beginning, less later on. So in the case of shrinkage, more detailed studies have been made, and the shrinkage loss has been divided into two subcategories. One subcategory is autogeneous shrinkage, CA. Other is drying shrinkage. So what happens initially, the concrete has a shrinkage in any case, and that shrinkage is autogeneous, that happens from within the concrete, and that is defined as Ca, which is smaller in quantity, and the bigger shrinkage is Cd, drying shrinkage, which happens over a later period of time and continuously keeps on happening. So both these things are calculated. I will not go into details of it because I'm seeing only 10 minutes left over. One thing important to notice here, both for shrinkage and creep, we find out something called notional size. Notional size is the ratio of the cross-sectional area and perimeter, periphery or perimeter. Now, if this ratio is, okay, if the perimeter is more, that means supposing you have a section which is I-shaped or something, then perimeter is more, area is lesser, the ratio is higher. When the surface area is higher comparatively, then the shrinkage and creep both are more because there's a larger surface which is available for atmospheric action to take place in terms of humidity connection and all. Therefore, this parameter, which is notional size, 2 into area of concrete by that's cross-section area by perimeter divided by perimeter. This ratio comes in the picture. As you notice here, if this value is more, means area is more, then we are somewhere here. So the loss is lesser because the perimeter is lesser, or ratio is lesser, more therefore, because area is more, perimeter. So like what I mean to say, if you have a circle, if you have a circular cross section, it will have the least perimeter for the given area. In that case, it will have the least loss of shrinkage and creep in that sense. And we have drying shrinkage, which is more. If you see these values, they are going to be higher than the previous values, and therefore drying shrinkage gives you a larger effect. There is a time-based effect, which is given in the formula here. There's a time-based effect of drying shrinkage as well, which is also given here. Then coming to the creep. Creep has one more difference, that apart from time, it also depends on the compressive stress that you've applied on the concrete. Sorry, I'm also sipping my tea same time. So stress in concrete, age at loading, that means when you put the load, when let's say you release the dead weight and live load and all that, when you apply the loading and for how much time you maintain it. So dead weight, of course, is maintained till infinity. So these are the parameters which come in the calculation of creep. On the whole, creep is higher than shrinkage. Now let us look at the comparison. We have shrinkage. Autogeneous shrinkage is lesser. Drying shrinkage is more. Creep is much more than shrinkage. But all these losses have to be accounted for because they are properties of concrete today at least, unless some new modifications come to the concrete quality which does not shrink or does not creep. And these are the time-based calculations which you do, elaborate calculations. Now, as I said, the losses can be less or more. What we do is a nominal loss calculation. But based on the actual properties of concrete, based on the actual content of cement and aggregate in the concrete, based on your type of sheathing wall, based on the quantum of rust in the pre-stressing strands or cables, many of these factors affect the losses. So since there is a variation in the losses, many times people felt that, look, my elongation is not reaching or my elongation is too much. So we say that, look, your structure must be safe for a 5% variation of losses in the case of, or rather, of the pre-stressing force in the case of pre-tensioning. In pre-tensioning, you have less variations because duct is not there, simple. In post-tensioning, 10%. So your design must be safe within this range of variation of pre-stressing force. Gamma superior, gamma inferior. I think I'll skip. Okay. Partial pre-stressing is not very common, but yes, if it has to be done, for 100% jacking force, the minimum concrete strength FCTR, which is whatever is required as per your design and as per the catalogs of manufacturer, you must follow. For 30% of jacking, if you do, then even then 50% FCTR must be available. Required minimum concrete strength. And if it's 30% to 100%, you can always interpolate between 0.5 and FCTR. Okay, for sheathing, again, there are stipulations in the code as to what should be the thickness of sheathing for stability, for reducing the wobble effects, and what should be the diameter of the sheathing. And when we say diameter, it is always internal. External diameter for this purpose has no meaning. There should be enough grout in the sheathing for internal pre-stressing and bonded pre-stressing that your strand is coated around with a thick layer of cement slurry. That's how a good sheathing diameter would work. It should not be too thin. If it is too thin, then around the strands you may not find any grout in some of those strands. In the case of SDP sheathing, the stipulations are different because thickness of the wall is more, but it is less stronger in that sense. And when you work out things like how to decide the subtraction of the duct diameter for thickness of the web for shear, etc., there you go with the outer diameter. So there, whatever loss you calculate on account of the sheathing is based on the outer diameter, not inner. This clarification may soon come in the code because it is just saying diameter. It may not say inner or outer. All right, so come to perhaps the last slide, I hope, is end block. I have seen umpteen number of cases where the end blocks have failed. In the past, there was a practice, talking of again 30, 40 years ago, that's my professional span so far, that end block was constructed as a precast member separately and brought into the site so that you could construct a very good quality and compact and vibrated properly and things like that. But nowadays that practice is more or less extinct, and we have these in the cast in situ right there as an end block. So the end block, the issue is that we have a good amount of force from the pre-stressing jack and the pre-stressing cable, which may be as much as, I don't know, 500 tons, 300 tons, even 700, 800 tons, each of the cable. Now imagine, just look at a building. Typically in a building, your column takes a load of 100 to 500 tons, 1000 tons. Even the column of a bridge will have 1000 tons, 2000 tons. Here at one point, you exert a force which is approximately 500,000 tons. It's a huge amount of force. So once that happens, and of course there may be many such, normally there are many such cables, anchorages at every about 400 mm or something. So when you do that, there's a good amount of compression, a concentrated compression, which tends to cause splitting of the concrete, transverse splitting. I mean, just imagine you have a concrete log, and on this log you apply a stress, it will tend to split transversely, perpendicular to the applied force. So when that tends to happen, you have to control it with the help of reinforcement. And for that, you design the reinforcement based on this formula given in the code. And you get this kind of either helix, or you can provide a square hoop, so that this core is confined against splitting. And it's very important. The two problems I have seen are either there's a failure here due to two possible reasons. One, that there's already so much of steel and the concrete is not compacting properly. Two, that this steel that you see as a hoop is not adequate, which also has happened and failures have taken place. Three, that between the anchorages, the distance is not enough. So please dimension that liberally, otherwise there are cracks here. And why there are cracks? Because between the two anchorages, concrete being an elastic material, it undergoes compression. Here there's a tension. At the next anchorage, there's again a compression. It forms a elastic curve like that. And if you forget to take account of all those tensile stresses in between the anchorages, again you can develop cracks, and I've seen such live example in Bangalore, let me tell you. So, and not only one, I have seen a few others also. So this is detailing in a pre-stressed concrete, especially at the junctions of this kind, which are concentrated force locations, is extremely, extremely important. You have to question yourself to do this. Okay, I think this must be the last one, I hope. Hyperstatic effects of pre-stressing. When you design a simply supported single span, you have a bending moment like this. You put pre-stressing going in the similar profile. It takes care of the tensions wherever they have to develop in the same profile. perfectly fine, no issues. But the moment you make it 2 spans or 3 spans, and you put some pre-stressing here, the effect of the pre-stressing starts distributing to this span and also this span, this location. As a result, whatever you put here, the effect gets reduced. So once the effect gets reduced, then you feel a bit surprised. Where has my force gone? That force is gone nowhere except for here and here. So what happens is that when you are short of, let's say, pre-stressing, supposing here, and you find that you require about 100 tons of force, and you provide a pre-stressing here, which is going to give you 100 tons after losses. But you may find that, look, my stresses are still not under control because only half of that was used. Remaining half has traveled here and here in a different form. Like this tension, compression here will travel as compression there, or tension here, and things like that. In the process, I want to tell you that if you need to improve something here, you may find that reducing the pre-stressing here is helping you more than by increasing the pre-stressing here. So be careful about this fact also. There's something called hyperstatic effect, which means you take a continuous beam, you apply a pre-stress, and this pre-stress distributes over the spans and over the supports. And what is that effect you have to study before you decide, because that part your computer doesn't do, that you have to do. So you have to know how the pre-stress is going to behave, especially in a continuous structure, through its hyperstatic effect, distributing effect in a indeterminate structure, which is the case here. So I don't know whether I went too deep, too fast. I have no idea, but I tried to square up. But I'm available as much as you want, as long as you want.
Thank you, Vinay. Thank you. That was, I'm sure all our budding bridge engineers and our senior bridge engineers, many of whom I see you in the participants list, are grateful for your presence today. I'm sure you've been treated to a treatise on the most essential things, many of which we always overlook. A few very simple do's and don'ts. For example, making sure that the tension between the anchorages, concrete is elastic, and between anchorages, tension may develop, and your RCC and reinforcement at the end at the anchorage zones is so important. And the other thing about durability and grout, all these simple do's and don'ts, I would say our Vinay has given us a gentle, easy way of understanding these things and putting it into sort of a story format rather than an absolute numbers and values and throw this at you and throw that at you. The issue is to understand the phenomena. The issue is to understand that some do's and don'ts. The issue was really, for what he highlighted was, what sort of protection you need to take, what sort of the kind of different types of pre-stressing would be. A simple idea was, for example, 200 girders. Now, if you have more than 200 girders, then obviously you'll go for a precast pre-tensioned system, fully precast beams, I-girder beams, like was done on Delhi-Gurgaon Expressway. Thousands, I think probably, I don't know how many, maybe 1,800 or how many girders were there on Delhi-Gurgaon? There were thousands, that much I remember. RTR Parliament, Delhi.
1,800.
1,800, yeah.
Largest in the country.
Largest in the, I thought, so I wasn't right. I wasn't far off that. So you can see then the difference. And dry joints and epoxy joints, when they are to be used, the hacking of the surface to have a good shear, interface shear between construction joints, especially at the diaphragm and the girder. All these are simple takeaways which you may not get in a book. It comes from experience. It comes from understanding of the phenomenon, understanding of, say, for example, the hyperstatic effect. It was very simply put to you that it would not be available to you in a computer, not easily available to you in a computer, right? Now, but the important thing is to understand it and to find out where, in fact, you may have to relieve some stress at one place to ameliorate the stress or to benefit the stress at another place. It's a balancing act situation in the hyperstatic effects. So all these were wonderful takeaways, for at least for me, as a refresher, as a reminder for all. So Vinay, with that, I would like to take some questions from the audience. But before that, Alok, would you like to add something? And then we can take the audience questions.
Yeah, I just wanted to say that it was a fascinating presentation, Vinay. I think nobody could have done a better job than you in covering the entire gamut of pre-stressing in such a short time. practically you have left nothing, and you have touched the nuts and bolts of pre-stressing, as one of the commentator, Mr. Hegde, mentioned. I see in the chat box, and I fully agree with Mr. Hegde. Excellent
Thank you.
presentation. And
Thank you
I
so
think
much.
this is a rare kind of presentation. Only a practicing engineer can give this kind of presentation. No academic institutions can give you anything, as detailed as this one, as far as the pre-stressing is concerned. I think there are many questions, and I would like the moderator, Dr. Subarao, to take questions.
Yeah. Wonderful. We have 60 questions, so I don't think we can do them all justice. And some of the questions being asked about whether we can share the PPT. Well, it will be a YouTube recorded version. I would like to remind our participants here that the similar type of talk was called A to Z of pre-stressing given in IIB. Both these will be available to anyone who wants to learn. The idea is to share knowledge in any case. So let us start with the first question. What is the lifespan of pre-stressing systems? Anonymous attendee, others I'll give the name. Go ahead, any of the panelists, just keep answering, yeah? What is the lifespan of pre-stressing systems? Go ahead, Alok or Vinay, just answer. What is the lifespan of pre-stressing systems?
Yeah, you see, the pre-stressing system is a part of the structure. So whatever is the design life, the system has to have the same design life, cannot be less. So essentially, I would say if the bridges are designed for 100 years, the pre-stressing system also shall be capable of, 100 years design life. It's an integral part of the structure.
You're right.
I think my direct answer to the question will be that it all depends on the designer and the constructors as to how they have planned everything in terms of the protection of the pre-stressing. It's all metal, and metal corrodes. So you have to prevent the corrosion and decide the life for yourself, the quality of workmanship and all that.
True, but the design life now, at least of 100 years, is to be
Yes.
ensured.
Yes.
As
Yes.
per the code, right? Does pre-stressing system require maintenance after service life? If yes, then how it is done? If I get it right, it is if it goes beyond 100 years. Is that the question? Does pre-stressing systems require maintenance after service life? If yes, then how it is done?
Right. So as far as the maintenance and all is concerned, if we look at some of the bridges not constructed properly, definitely we have seen problems. For example, we discussed a bridge in Karnataka, wherein through the endoscopy, they came to know that there was a problem. But of course, much before that, there were cracks and spalling of the concrete. But nowadays, our quality of workmanship, our specifications of construction and specifications of design have improved quite a lot. And therefore, once you follow all this, the code says that you can assume a deemed life of service life of 100 years. But yes, one has to keep on inspecting, and to see any sign of distress, any sign of crack, any sign of spalling of the cover, and immediately attend to that by hacking by NDT and other things, and repair, rehabilitate, and then elongate the life. It's like you have a life that goes on and on, drops, then you do some repairs, it goes up and again increases. So likewise, we can keep on elongating the life, because nothing is permanent in this world, that we know very well.
I think the question comes from the fact that many pre-stressed bridges have now gone in for further external pre-stressing or a sort of a repair retrofit approach, which is seen. The point really is that the losses of pre-stress are there, the issue. And if the losses are high and say too high and not anticipated beforehand, a priori, when you do the initial design, then we may land up in a situation over time where we may have to intervene and add additional external pre-stress. Yes. So, and that will again get you back the whole idea of keeping alive that structure to achieve its design service life. That's it.
Dr. Subarao, if I may just add, in response to the earlier question about the, protection and life of pre-stressing system, I just wanted to mention that though in our IRC 112 we do not have the classification, but the European codes have the classification depending upon the exposure condition, what kind of protection system they have. They have PL1, PL2, PL3. And I think very soon in IRC 112, we are going to introduce something similar to that.
Yeah.
So at present, we do not have this well defined in the code. But if you have a pre-stressed bridge, let's say very close to the coastal region where the environment is aggressive, you are supposed to have a different corrosion protection system on pre-stressing than if you have a bridge, let's say in Delhi.
True.
So that is one thing. And second, about the maintenance, I mean the to increase the design life of the bridge, many bridges have failed because of the corrosion of pre-stressing steel. Vinay mentioned about Sharavati bridge in Karnataka, but the Mandavi bridge collapsed in 1986 primarily because of the corrosion of
Corrosion
the
of cable.
steel.
Yes.
Right.
So there are many such examples. So inspection, routine inspection, and maintenance should identify these issues and address.
True. True. Let us move on. What is the use of grout between duct and cables as the cables are not in contact with concrete? I think that's a bit of a, anyone. Go ahead, Vinay.
Okay, as I said earlier, the grout that we provide is for two reasons. One reason is that it's full of cement, and cement has a pH value of 13 or 14, depending on the type of cement used. So this high pH value keeps a passive environment around the pre-stressing cables so as to maintain a good durability. Number one. Number two, cement, when we provide between the cable and the duct, it creates a continuum. That means from pre-stressing cable to the duct, there is a cement, which is like concrete, but without any aggregate. And then from duct to concrete, anyway, it is concrete. So this becomes a bonded system wherein the cable indirectly is then connected to concrete as a bonded system, wherein the strains in the pre-stressing and in the concrete are the same everywhere throughout the length.
Right. What is the, Naveen Kumar Tipudi asked, what is the unbonded length in a pre-tension girder? I mean, is there some means to ascertain that value or some design approach to it? So we
Yes.
just have to point him in that.
Yes.
Go ahead.
When we carry out a design, we find that towards a support where the bending moments are lesser and the same pre-stress is continuing as at the bottom, at the mid-span, this becomes over pre-stressing for near the support regions. So there we have to demobilize some of the pre-stressing, which can be 4 meters, 5 meters, for some of them 2 meters, for some of them even 6, 7 or 8 meters for various strands. So this debonding is provided so that we have lesser cables available with the full eccentricity, of course, that cannot be reduced at those locations. And simple procedure is that we provide a SDP tube around the strand, and this tube separates the strand from the concrete because there is no cement grout inside this SDP tube, which is 20-30 millimeters in diameter, around each of those strands which are unbonded. Others are bonded.
Right.
It's like that.
Under vibratory load, Mr. Jaiswal asks, can unbonded strand vibrate relative to main girder? Has any such case come to notice? Natural frequency of strand will be different in such cases than that of main girder.
The interesting question, that the strand which is inside may vibrate if it is unbonded because it is housed into a duct and the duct is outside the concrete. I think we are talking of the external pre-stressing.
Yes, external pre-stressing.
So there's a stipulation that at every 12 meters minimum, I mean the maximum distance of 12 meters, you must have a deviator block, which means even if the cable is running straight, even if there is no deviation of the angle, you still have to have a deviator block controlling the duct vibration, or carry out a detailed vibration analysis for which stipulations are not there to my knowledge.
No, there are
so just provide it every 12 meters and be done with it.
That was a good question.
But there is a question which is very relevant.
Good point.
Yes.
Bidan Roy asked, what is the minimum radius of curvature can be provided on a post-tensioned cable?
Right.
Minimum radius of curvature.
Right. Now, let us understand why we are talking of this question. The minimum radius of curvature of a pre-stressing would depend on what concrete can take mainly. Pre-stressing will fail much later. It can go up to very sharp angles also. It will not fail. But it's a concrete that will fail. So when we have a sharp curvature, we have a bearing stress on the concrete. Sharper the curvature, more the force in the radial direction, and more the force in the concrete for it to crush. So it is based on this that the stipulations are given as standard values in the code that you can follow this. There is also a formula, and there is also something in Rourke and Young, if I'm not wrong, or maybe Park and Paulé.
Park and Paulé.
Park and Paulé. You follow those and see that your concrete is safe enough for that. If not, then code also tells you that you have to provide cross steel around the cable duct to hold it against going into the curvature. So yes, it's a very pertinent question. It's purely on detailing. That's very important.
Then let us take, what is the difference between T and K when you say 19K15 and 19T15? What is the difference?
Right. It is just the supplier's designation. Right. Some suppliers would call it T-range jack or T-range jack, basically based on T-range jack, and some people call it K for different suppliers. Some suppliers also have C-range jack. Ferrezne is a newer invention about 30 years ago was C-range, where the jack is shorter. Yeah. So it's just a supplier's designation.
Right. What are the minimum days you have to wait for grouting as per the code? So when do you grout? This is probably posted. When do you grout?
I'll reverse the question. I will rather say, don't wait. You pre-stress today, you wait for a day. After one day, you cut the strands at the back and grout as early as you can with a maximum of 14 days. But you can grout after 3 days, after 4 days, after 7 days, earlier the better. Because what is happening? Initially, a pre-stressed concrete structure, when you stress, is unbonded. But is that your design? No. The design is bonded design. So you must bond it as fast as you can, as early as you can. And protect the steel also against corrosion. So both the advantages.
What is the limit? Shivakumar Alapka asked, what is the time limit for between the stressing and pouring in pre-tensioning?
In pre-tensioning.
And then you pour the concrete in the pre-tension,
right,
in the casting yard.
Right. In pre-tensioning, time limit purely depends upon the gain of the concrete strength. For example, if you have M40 concrete as a design concrete, and you really pour M40 concrete, whatever the ingredients. But for the pre-stressing, you may require about 32 MPa to be safe or 30 MPa to be safe. So you will wait till the concrete gains 30 MPa strength by breaking the cubes and all that. And moment it does that, you can then release the jacks to impart the pre-stress. If you remember in Delhi Gurgaon project, Dr. Subbarao, our contractor, although the concrete gate designated as M40, they produced M50 so that in lesser number of days, they could get 30 MPa and they could stress the cables, or release the cables.
Okay. Then Nazrul Imam asked, what is the advantage and disadvantage of external pre-stressing in case of eye girder? At what situation external pre-stress is required in the case of eye girder system?
Right.
This is the question.
Now, external pre-stressing, if you talk of the original structure, in eye girder also it can be provided. But thing is that this will be seen outside. It will be visually not a very good structure to see. Whereas in the case of a box girder, at least it can be housed inside. But what happens is when you provide an external pre-stressing, especially inside a box, the pre-stressing CG is not as much. It's higher up. So it's closer to the CG comparatively, and therefore you get a lesser benefit of the pre-stressing, and therefore you get more pre-stressing quantity. In the case of girder, you can put it at a better CG. You can go till the bottom, but then they'll be visible outside. They will require a larger protection against corrosion. They will require external type of SDP ducts anyway, which are thicker and no metallic sheathing. So normally in India, at least I would say, it has been used, the external pre-stressing, more for repairs when there's a failure. Right. Very few structures do have external pre-stressing, no doubt, but that's how it has been.
Right. For a post-tension concrete from life cycle point of view, what is more economical way of grouting, with cement slurry or anti-corrosive compound like grease or wax, or could they also be used? Is only cement grout used, and is it more economical?
Yes, I think when the quality is good, then grease or wax will have a better protection against the corrosion of steel. But when we talk of the cost, there's a very large difference between that and cement. Cement is expensive, but much cheaper than grease and wax, and therefore people tend to go for cement. Look at the other side of it. Cement is brittle. You provide cement, and if it's external cable, the brittle cement cracks at various locations due to elongations and contractions and all that. Whereas grease and wax are flexible materials, they will not. They will be definitely superior, but the point is that they're much more expensive. So internationally, anywhere, people still are relying on cement itself. That's my
Right.
view about it.
Right. This is a very pertinent question, Mr. Satish Dupele, one of our senior most structural engineers
So
in
I think
India.
Mr. Alok Bhamik is having some views on this. Did you want to say something?
Alok, anything?
Yeah, I just wanted to say that, one advantage of using grease in external tendons would be that there is a possibility of replacement
Replacement. Yeah.
of
Repairing
the
and
of the
replacement.
of strands in the cable, which
Definitely, yeah.
in the cement ground you will not have. So you have to basically a trade-off between initial cost vis-a-vis the advantage.
Yes.
Right.
Yes. Satish Dupele sab asks, in case of segmental construction of JJ flyover or a viaduct, care probably was not taken to incorporate super elevation around quite a few bends, resulting in obvious flying off of two-wheelers around the curves and hence banned. The two-wheelers are banned on this JJ flyover. Besides this, speed of four-wheelers too, as of now, has been reduced along these bends to nearly only 30 kilometers from what was supposed to be 60, 70. Are these not usual problems of segmental construction, or was it a feature not addressed to during its design, detailing, and construction? So it's not a particular dig, but this is a city in which we both live and in which this flyover has been limited in its speed. Could this have been a design issue which we should have designed out at start, a matter of super elevation, or is it a problem in this type of construction, the constraints of the site? That is the issue being raised.
Let us be very clear. It is not a problem of the technology. It could be a problem of the initial designs not done properly or the construction not done properly, one of the two. Of course, I'll not be right in saying any of these.
Right.
Is that one did not follow the highway curvatures, super elevations properly, and therefore you have a problem. Maybe they were underestimated the super elevations or something.
So the geometric
but it's
design.
Not a technology problem at all per se. That's
So maybe it's not a consequence of inadequate addressing of the geometric design requirements.
Yes.
Or during construction, the geometric design requirements were put aside due to constraint issues and so on. But that has led to a limitation, which is very.
If it has to happen, it will happen in Kasan City also.
Yeah, it will. Okay. Now, Gaurav Patil asked, please explain the difference between creep and shrinkage. I think, Gaurav, we will let that pass because that is both are time-dependent phenomena, and it was touched upon, and you will have the recording of this presentation. So get back to us after you go through again and get a little bit more on the basics of creep and shrinkage. So we will leave that for the moment. Are these recommendations for residual stress valid for all locations, center and end in a girder? Are the recommendations for residual stress valid for all locations, center and end in a girder?
Residual stress means, are we referring to 0.75 FPK or something?
Yeah, would they be at center and end?
Anywhere, over the length of the pre-stressing. Yes.
Right, over the entire length.
Yes.
Can we apply 80% of UTS while stressing, but 0.765 of UTS? Can we go to 80% of UTS while stressing?
If the sentence is can, yes, you can. You can apply 110 also, can. But should we? Are we permitted to? If that is a question, then I would say, since code has given a safety recommendation not to exceed 76.5%, we should not. In the past, people have done it though. And some of the pre-stressing used to fail also more often in the past. People have gone up to 80%, I know. But based on the experience and other things, these provisions have been modified and we should respect these provisions.
Okay. Pre-stressing and post-stressing is okay for beams. We all know that. This is Professor Mainik Ghoshal asking. But could you throw some light on pre-stressing or post-tensioning for slabs? Actually, how are they done in real life with examples in India?
Yes.
Is it for slabs like, our bridge slabs, our building slabs, like the hotel you pointed out? Is it done directly for the slabs?
Yeah.
That's the case.
Let us understand one thing, that post-tensioning can be for precast as well as cast in situ. Whereas pre-tensioning is only related to precast. So if we talk of post-tensioning, of course, I think we all understand in buildings, in bridges, everywhere you can use and you've been using. But talking of the pre-tensioning, there are very good examples that use pre-tension hollow core slabs in buildings.
Yes.
In bridges also we use pre-tensioning, of course, quite often we have seen. Now, if you visit any of the precasting factories like Precast India Limited in Pune, which I visited about a year ago before the lockdowns, they have a fantastic method of doing this pre-tensioning of hollow core slabs. They make a long length of 100 meters, make it, and once it hardens and everything happens, the pre-stretching is released, then they simply saw cut.
Yeah.
And by saw cutting, they get fantastic speed over. So
Wonderful.
it's a part of building this way, precast.
Okay, good enough. That's fair enough. Balance cantilever and segment construction, which method is more suitable in city area in terms of speed, safety, and economy? Let's ask Alok to answer that. Balance cantilever and segmental construction, which method is more suitable in a city area in terms of speed, safety, and economy?
Actually, mostly overhead launcher with cantilever. If you are talking about span by span or cantilever construction,
Either
exactly what?
it's balance cantilever versus segmental,
No, you see,
which is more suitable in
mostly
city area.
mostly in city area, you go for span by span construction with overhead launcher. That is the key. Only in very rare cases you need to go for cantilever construction where you have a long span to cover. Very few cases we know. There we have no option but to go for a cantilever construction. But by and large, if the spans are in the range of 50-meter maximum, we can go for span by span construction.
Right,
I'll
right.
add to this.
Add to that, I was going to suggest,
okay.
Vinay, you please add to it. You please add to it from the other
Okay,
side.
I'll add to this. What happens is that cantilever construction, you don't use it by choice.
Exactly.
You use it by compulsion. When either the span is long or the pier is too tall to provide anything from ground, or if there is a structure below like a flyover below and you are bridging over a flyover.
Or a
You
ROB.
will,
Or
or
a
a
rail.
ROB, where you can't support on the ground, you will go for cantilever construction. And normally in a balanced cantilever construction or cantilever construction, the cost is more. Whereas precast segmental, if it is simply span by span, shorter spans or moderate spans, it is faster, cheaper, and regular, and that's how you will normally do. So cantilever construction, you don't see the entire bridge somewhere being constructed by cantilever construction unless it is in a river or sea or something like that. Those reasons.
That's a good answer. That's what I wanted. Right. Is there any advantage of metallic duct over HDP? Does the metallic duct, does it have any advantage at all over an HDP duct? Is the question being asked.
Cost.
Leave it at that.
And of course, I will tell you, metallic
duct is outdated, I think. But now
yes,
is
metallic
most
duct is more
countries.
easily
Most countries, it's
available.
not
It
used
is cheaper, but it's full of joints. Every 3 millimeter, every 3 centimeter, there's a joint because you make strips like this in a machine.
Vian Hegde, who's our CEO of Stoop now, a dear friend again of all of us, he suggests that, rather he comments that in excellent explanations, bolts and nuts of prestige explained so lucidly that will be understood by a layman. Great work done, Vinay. There you go. That's some praise.
Thank you, Mr. Hegde. How are you?
What is the impact of low, Shivakumar again asks, what is the impact of low temperatures in strands while stressing? So if it's very cold and you're stressing, are there some do's and don'ts situations, in Kashmir, in snow or whatever, very cold? Is there difference between doing it in a warm area than in a cold area?
Yes, I think let us understand that at low temperatures, steel tends to become more brittle. And we don't like brittleness in our steel. For example, if we talk of structural steel, in the sub-zero temperatures, we have to use that C-grade steel, which is low content, the more controlled carbon, magnesium, sulfur, silicon, phosphorus, etc.
Correct.
And so for it to remain ductile and all that. But in the case of pre-stressing, we don't deal with that level of ductility. In pre-stressing steel, what happens that the elongation at break is only 3.5% as minimum. It is not 14.5% or 15% like in the reinforcing steel. So at this level, even sub-zero temperatures, the normal pre-stressing steel is fine. No modification is necessary because we don't expect that ductility to that level from pre-stressing steel, which we expect from reinforcing steel.
Righto. So the ductility is actually an issue for the reinforcement, and it wouldn't be such an issue for the strands at low temperatures.
I would say more so for structural steel.
More so for structural steel, yeah. Can FRP tendons be used in place of steel tendons?
Yes. Enough research, not enough I would say, but ongoing research is there on FRP tendons, though they are frightfully expensive compared to metallic strands, but they require lesser protection, they have a lesser life. But the research that is mainly going on is how to anchor these, how to stress these because they require a different kind of a gripper to grip it, not as simple as you have a wedge and wedge bites and the strand is stable. So those are the research work that is going on. But if we talk of FRP, pre-stressed FRP, especially in retrofitting, what Dr. Subbarao you also do,
Right.
is that in the case of
Laminates.
retrofitting, FRP laminates, which are in terms of plates, are stressed and placed onto so there are different grippers for it through which you do. But in the bridges, the application is very heavy. So it's not so easily and commonly used. We use these FRP, what do you call it, rebars for our metro structures where you have to cut it. Shear strength is low, so you can cut it more easily in underground metro.
Right.
Diaphragm wall.
Diaphragm wall constructions, yeah, where you have to punch through.
Right.
Yeah. The other point, of course, is that FRP laminates also, suppose you have loss, very high loss of pre-stress in the order of 10 to 15% in a structure over time, it is not possible to make these up with simple laminates. The demand is too high. So the laminates and the wraps act as a secondary backup, as an additional measure. You have to resort to external pre-stressing if we have very high pre-stressing losses, please note. Now, Likon Biswas asks, IRC 112, table number 7.1, what is uncoated stress relief strands? Is it unbonded?
Yes. You see, this is a part of the manufacture that these strands are put through some process called stabilizing. In the stabilizing, the strand, after regular manufacture, it is passed through a chamber with steam at 400 degrees centigrade temperature. And it passes through that, and the next chamber is cold water, regular temperature water. So it passes through that, and that stabilizes, and that also does the relaxation, what do you call it? What is the word you said? It does that to the pre-stressing cable. Unless there is something more than this, I could be missing out on that.
Yeah, it's unbonded. Okay. Nitin Bansal asks, how do you differentiate between pre-stressed and bonded post-stressed design in terms of transfer of bond stress from tendon to concrete?
Can you repeat the question? How do you distinguish
between pre-stressed and bonded post-stressed design in terms of transfer of bond stress from tendon to concrete?
Okay.
The issue of probably, I think he's meaning the
pre-tension and post-tension.
Pre-tension and post-tension, the difference in strain, the concept of strain. Yeah.
Right. As far as pre-tensioning is concerned, it is very similar to reinforcing steel, but for the fact that we have an active force and each of the strands not into any kind of a bond, any kind of a duct or grout, etc. It is just directly in contact with the concrete, and therefore certain things change in terms of requirement of the thickness of member and all that. In the case of post-tensioning, we do have a duct which is fairly large in size. It may be 100 mm, 150 mm or whatever. And inside that we have the cable, and around the cable we have a grout. Now once we have cable, a grout, a duct and concrete around, it becomes a bonded system because it is tendon or pre-stressing cable to grout, to duct, to concrete. And I think if the question is also about unbonded. In unbonded, what happens is that there's a slippage between the concrete and the pre-stressing cable. There's no direct marriage between the two. At the end of it, only at the end of the member, they have a marriage, but in between there is no marriage. So the strand or the cable can slip or can have its own strains within the two anchorage points, and it will have, because the CGs are different. Concrete girder CG is somewhere towards the center, and that of the cable is below, and therefore the strains are different, and they're free to have different strains. So the design changes.
Right. It's also the issue of strains, right? Because the strain, an externally bonded, an external cable is not housed inside the concrete. So its strains will not directly be compatible with that of the adjacent concrete. There are different levels of strains at the same cross section, if you consider. So there's a difference in the design for sure, right? About the performance of pre-stressed structures during earthquakes in India and elsewhere, how have they performed? It's a general question being asked by Prince Doshi. Are there any demerits or any special do's and don'ts for considering pre-stressed structures' performance during earthquakes?
It's a very good question. And really speaking, I've also been thinking to myself about it. What happens is that when we have a structure, a pre-stressed concrete superstructure resting on bearings over the pier, we do not see a problem because the earthquake forces don't transfer to the structure, superstructure, except for maybe vertical earthquake and all that. But when it is integral without bearings, then yes, everything is directly transferred to the superstructure, and certainly ductility of that structure is not as much as that of a pier, which is RCC. So there's a cause for worry. And I really do not know what exactly we do for this to make up the ductility loss that we have in the pre-stressed concrete, unless anybody like Mr. Alok or
Alok,
Mr.
anything to add, Alok, on this?
Yeah. I
And
think
integral also. Yeah.
that's a pretty good question.
Yeah.
Firstly, there has been a sort of as far as the segmental bridges are concerned, there is a lot of concern in many countries to use segmental bridges in high seismic zones. Though in India we are using it quite extensively, and many other countries do use that. But there are countries like Germany, I think, or
Yes, Germany.
they do not use segmental bridges. They have almost a ban on that.
Done, yeah.
As far as I mean, the point which Vinay mentioned is right, that because of the lack of ductility, there is a problem of pre-stressed concrete bridges. But you compensate for that by, if you recall, Vinay and Harsha,
By
in IRC
solution.
18 we used to have a provision that in case it is in the ultimate stage, if the failure is due to the compression rather than tension,
Tension.
we used to have 15% extra margin. So
Right.
there used to
Right,
be a
right.
provision in the previous codes,
Right.
and I think the if there is so you have to have extra margin in ultimate limit state. But good thing is, mostly the pre-stressing is used in the superstructure, and the
Yes.
earthquake problems are more related to substructure and foundation, and superstructure is only a problem of dislodgement. As such, the superstructures are designed for as an elastic material. I mean, it is not, ductility is not considered at all in the superstructure design nowadays. So all these factors are there as far as the pre-stressing is concerned.
In a way, it could be argued that introducing a bearing for an integral bridge compared to an integral would be here an advantage in some way against a seismic situation, or would we have the ability to dissipate the earthquake energy in some other way in an integral structure? I mean, where the pier and deck are fused without a bearing,
You see,
monolithic without a bearing.
unlike buildings, where the philosophy is that in a integral kind of a structure, your beams should fail first and not the column. Unlike that, in bridges, it is the other way around. If you have an integral bridge, you
Absolutely.
have to ensure that the column at the junction, it is the column which should fail first, and indirectly that means you have an extra margin which gives you margin for the deck. The superstructure should not fail. So, and the normally the pier at the junction is basically an RCC. It is not a pre-stress generally,
So the
by and
plastic,
large.
so we enhance the plastic ability at that junction
Correct.
of the by increasing the confinement and ensuring the close spacing of stirrups, etc. We try and increase the plastic ability at the junction area, in the column,
Yes.
column
Yes. In
where
the
we
column.
want it to hinge, not in the beam,
Yes. Not
like
in the beam.
yeah,
We ensure that there
unlike a
is
building.
correct. So we ensure that the beams have more. It hasn't got an overstrength over the the plastic hinge formation at the column.
Right. A very important question Rahul Kaurav asks again. What is the demerit of external pretensioning? And what is the reason that external pre-stressing is not used in India to that extent? And why is the late adoption and introduction, or is it generally a worldwide phenomenon?
Yes, it's a, I would say, worldwide phenomenon as well. External pre-stressing, if you put it in a girder, as I said, eye girder, you will see it outside, you don't want to see. If it's a box girder where it can go into the hollow space of the box, the disadvantage generally is that the cable cannot be into the bottom slab. It cannot be as low. It has to be higher than the bottom slab to clear the bottom slab, be inside the hollow space. Therefore, the CG effect that you get, the eccentricity which you get from CG of the box to the cable reduces drastically. It reduces substantially because the whole CG, let's say if it's 1 meter and you have taken it up by 300 mm, you're losing 30% of the eccentricity. So the number of cables, they increase. But on the other hand, the advantages, if you see, if it's a precast segmental structure, you don't necessarily have to provide epoxy. You don't necessarily have to provide temporary pre-stressing. Although in Indian code at the moment, we are holding on to this decision.
Yeah.
But that could be the advantage. That is the advantage. And therefore it becomes faster, speedier, what we experienced in Malaysia and Metro.
What you said, yeah.
So it's an analysis we must remember before we decide what we want to use. Merits, demerits, weigh over the two and decide one.
But Alok, is there some reason? Yeah, go ahead, Alok.
Yeah. So I think Vinay has put very nicely.
Yeah.
The key points are, what are the advantages and disadvantages of external pre-stressing? The disadvantage is that you need more pre-stressing cable because the CG of the cable is up, but there is a reduction in the thickness. There is a material saving of the element because your web thicknesses can be much reduced because you don't have a duct inside the structure. But most importantly, the external pre-stressing is the one where you can avoid epoxy. The dry jointing is only permitted if you have external pre-stressing, and that is what is going to drive where external pre-stressing is to be used. If you have a very long corridor of elevated, let's say about 8-9 kilometers, then even if you save, let's say, 2 days in erecting one span by avoiding epoxy jointing, and just imagine if you have 8-kilometer long elevated corridor, definitely external pre-stressing will be the solution from consideration of the fast tracking, and that will outweigh the other disadvantages in terms of material economy. And there are quite a few, I think, corridors in India where external pre-stressing with dry jointing has been done successfully. Of course, there are some countries where this dry jointing is almost banned.
Yes.
Because of the workmanship problem. And I think in IRC, we have not banned, but we have not promoted. We are remaining silent on dry jointing.
But Mr. Bhaumik, exactly extending your answer, in Malaysia, in this 26-kilometer long LRT2 that we did, the only consideration when we asked them for using dry jointing and external pre-stressing was exactly the time. They said they save one span per day.
Correct.
1 day per span, sorry. That
itself
was a big saving for them. We never thought of that because 25 years ago, we never knew the importance of time in a bridge. they taught this to us. So, and the other advantage is you can replace it.
Yes.
But let me also get the worry. The worry was that somebody may cut the cables by blasting, bombing or something, and the bridge may fall on the lighter side of it.
In Kanakadurga flyover, which was done by ACOM, and we were doing the proof checking. It's a very long spine beam. We have used a mix of, we're going up to 40-meter spans, and we have used a mix of external and internal ducts, So that's, I don't know whether it's like a hybrid situation which we came into.
Well, that is a very good idea. To have a hybrid kind of a thing, partially internal and partially.
It's a beautiful.
They do it outside India. They do.
We did it here. It's built and commissioned now.
Right.
It's about 3 odd kilometers long. I don't remember. It's a very long one. So 28.5 across, or 28 point something across, 35 or something across width. And they have used this, and we've gone up to 40-meter girders, etc. So it has been done, but it was wet joints. Yes, it was all wet joints.
Okay.
No, but I think if you go for dry jointing, your requirement for quality control has to be
very high,
much higher than what we have now.
Yeah.
Well, Dr. Harshavardhan, your father told us that when you do dry jointing, you have to also worry about from which direction the sun is prominently coming. predominantly.
Yeah.
because it
And
will
the
open
segment may have
unequally.
a small distortion.
Yeah,
Yeah.
because it hits one side and unequally open. Yeah.
Yes.
So there is a question by Vijay Krishna. I'm not sure if it's connected to this, but he's asked repeatedly. Would be grateful to your goodness if you could kindly say about circular pre-stressing, its anchorage systems and the losses in it. Now, circular pre-stressing is used obviously in a circular type of structure. I'm not sure if he means about the U-type vertical pre-stressing, which we use in in accelerated bridge construction through the U-shaped cables for the pier integrated into the to integrate the precast uh, foundation with the pier with the starter piece for the superstructure. We use that vertical U-type pre-stressing. I'm not sure if he's talking about that or whether it's the circular pre-stressing we use in a nuclear containment vessel or a silo. I'm not sure which one. So you comment on it, whichever you.
In the silos and chimneys and all, when they provide this, mainly in silos, then what they do is that they take one single cable around and then they crisscross at the anchorage. So there are two separate anchorages. There's no very special system. Yes.
Right, right, right. Okay, let us go to for grouting of HDPE pipe in post tensioning. Mr. Pant is asking, what should be the strength of the grout? After grouting, how many days will it take to remove the bottom shutter?
Okay. After the grout, it should gain sufficient strength. Well, bottom shutter can be removed anytime.
Yeah.
There's no such criteria. You can even remove the bottom shutter after pre-stressing and grout it later on.
Later on.
But the strength of grout, if I remember correctly, is about 40 MPa.
Right.
If I'm not wrong, I could go wrong in the picture, but I can recheck my slides. Is about 40 MPa.
There you go.
But you have a high strength grout also. For if you have a concrete which is M75 and M80 and all that, then there are high strength grouts as well, which are special formulations.
Now, Mayank Ghoshal asked, given the high amount of construction in India, we see less number of comparable precast construction with respect to cast in situ construction. Could you cite the reasons apart from politically sensitive cases? Actually, I'd just like to add one point here before I throw it to the panelists. The point really is, it is all precast. If you see the metros, there are huge casting yards, and all the superstructures precast in most of the metro constructions, except for some very difficult spans, which may be particularly highly curved or some local situation. Then it is dealt with a cast in situ type or balance cantilevers, a cast in situ type construction, but not otherwise. It is impossible to do large metros without full precasting. Any large structure without full precasting is impossible. The typical rule in, say, a road bridge is if you're about 30,000 meters square of deck, anything beyond that, I mean, you're into segmental construction. Segmental is automatically precast. That type of segmental construction is precast construction which you could use. So these are all thumb rules. It will depend on situation to situation. But on the larger point, Alok, you and Vinay also know that there is a thrust from the ministry at the highest level. We are debating the use of very high amounts of precasting for every kind of bridge structure in India. Prefabricated steel structures, as well as the prefabricated precast factories all over India type approach. You order it on the phone. You order like you have in the US or you have in Europe. You have precast factories and you have numbers, and you just dial them up the local area. They transport to about 100, 200 kilometers radius, and they give you a ready-made product to site to use for your superstructure or your piers or whatever you want precast. The question is that why is not that adopted in a large scale in India?
No, I would put it like this. There are merits and demerits in both. In cast in situ, apart from the demerit of the time, there is also a demerit of quality because you're working at site and pouring the concrete there. There can be issues of concrete pouring, quality, compaction, etc., etc. In the precast, you at least produce faster. You produce in a factory-like condition where your quality control is on an average better. But demerits, that there are joints after joints. So we are trying to make up the deficiency that is created at the joints by various methods, call it epoxy jointing, call it temporary pre-stressing and so many things, and couplers in the ducts and all that. So once we have done this, we have got a very good concrete, that's factory quality concrete, and we also have the speed, and we have taken care of the joints. I think we have done our job, and that is the reason why precast segmental is becoming more and more popular. I would rather say, on the contrary, popular as against cast in situ. Secondly, cast in situ has a disadvantage also of the environment. You'll be casting it in the urban area for a flyover, and you'll be, dust and cement and everything flying in the sky. Whereas precast is at a designated place, and you are able to control things better off at one single place, and you bring it to the site. So a lot of these advantages are there. Only demerits, I would say, are joints. So we're trying to deal with joints in the every possible way to reduce this weakness, and everything else I think is an advantage.
Right. Alok,
I just wanted to add
yeah,
something to what Vinay has said.
yeah,
You see, Harsha, you touched upon this issue of that ministry is now coming out with a policy
yes,
on
yes,
precasting on a very
yes,
large scale, on
yes,
a factory scale. And I mean, there is a roadmap. I'm aware
yes.
of this because I'm a
You're,
part of that think
so am
tank.
I. That's why I asked you, me, Mahesh,
So,
all of us are part of that advisory. And the document is
yes.
being just circulated to us. I wanted you to
So,
bring that up.
so that I mean, if you are comparing between a cast in situ and a precast not only necessarily means segmental. It can be a girder precasting.
Exactly.
We are thinking of now having a ministry of standard. I think
Yes.
Mr. Hegde is involved in developing ministry standard for spans ranging from 12 meter to 32 meter for all kinds of widths, 12 meter, 2 lane, 3 lane, 4 lane, up to 8 lane.
Right.
And this kind of standardization with a policy for, industry based precasting
Right.
is the basically way forward. So basically, we are thinking of a situation where the contractor will simply order a number
On the
of
phone.
X
Yes.
number of girders of
Exactly.
by number of span on the phone, and he should get it delivered.
Exactly.
So we are looking for a situation where within a particular radius of maybe say 40-50 kilometer, there is an industry, and that is the kind of policy and the
That's
thinking
right.
which is going on.
That's right.
And in fact, the future contracts are likely to have mandatory provisions to have, particularly bigger major contracts. There will be mandatory provisions where the contractor has no option but to go for a factory produce. He has to put
Right.
factory.
Right, right. That's the point I was making. Or it might become a private enterprise where you open your own store and you can
Yeah,
supply these on demand. That's the
yeah.
whole idea. That is how it is elsewhere in Europe, and even in America. You have
Mhm.
standardized astrogirders which are
Yeah,
produced and sent off.
That's right.
yeah.
Yeah.
You just order them.
Yeah.
So, okay, coming to the how do you Rahul Kaurav asked number of questions. I'll just pick up one or two, Rahul. How to calculate additional effect of creep due to pre-stressing as well as dead load in case of a continuous structure?
I think we will have a refresher course on
I
this.
will that I no, but I just wanted to put the question to. He has asked number of questions and all very important questions, but each of them will require an in-depth answer. So I think Rahul, you may excuse us, but we acknowledge the very importance of your
I
question.
think we should request Mr. Rahul to deliver a lecture. Sure, he must be having answers.
Okay, Arun S says it was nice to go through it and refreshing the basics. Thank you again. Praises. Ramesh Ravuri asks about the bowing. When the structure is pre-stressed and it bows upward, then this bowing, are there any measure how much it should be? Is there some limiting values after pre-stress? Then you put the deck slab and the wearing coat. Now, how do you calculate how much compensation will happen thereafter also? So what is
Yes.
the calculation method?
See, all these are items which can be calculated and which are calculated in most of the cases where we have the dead weight acting downward, we have SIDL acting downward, we have pre-stressing acting upward if it's a simply support span case, and we do calculate. But the point is that these deflections are so very small. They are in the range of 3, 4, or 5 millimeters. They get covered up in the bearing course thickness. The bearing course may be as much as 50, 60 millimeters. Otherwise, yes, vehicle can bounce up and down if there is an issue, but we do level it up at the day of opening to the traffic. At least on that day, the structure must be level. Later on, again, the deflections will take place, creep, shrinkage, and again, the structure will tend to go down, but maybe also put bearing course every 5 years. So it's a very intricate question to answer.
Right. So, but there is guidance in the code regarding the values that you have to attempt to achieve and the limits on them. Yeah.
They're only against live load
Against live
reflections
load. Yeah.
in chapter 12.
Yeah. So, sir, please share some design examples. Alok, there you go. You have to have a workshop on design examples. There you go. It's been
Yes,
asked
very
straight away.
much. Very much.
Now, so I think we will do that. We will concentrate. The codes are undergoing some revisions and modifications currently, and some important changes in 112 and IRC 78 and IRC, some of these bridge codes,
And
and
IRC
similarly
6.
on IRC 6 a lot. So we will come back to you with all that understanding and structure for you, some design example courses taking into account all these changes. There is a need, we see it, and we will satisfy that need in the near short term. Shaukat Hussain asks, what is the load balancing effect in pre-stress concrete? What is meant by load balancing effect in pre-stress concrete?
Load balancing effect.
Yeah.
I'm trying to
American jargon, probably.
gather the question. What is load? Of course, if at all I can understand something out of it is that you have a downward load acting on the structure, and that load is being balanced by the pre-stressing by pushing it up.
Yes.
That's all I can understand. And we provide almost the same amount of pre-stressing stress by pre-stressing as much are the loads on account of the dead loads and SIDL and live load.
Right.
Broadly.
Right.
But we still leave some more residual compression for other factors like temperature, difference in settlement. That's all I understand by this question.
Right.
Load balancing.
Okay. Is post-tensioning system, once the stressing is done, do we really require to wait for 24 hours to measure the additional elongations? The elongation waiting of 24 hours, is it required?
Not really though, but there can be some slippage of the wedges, and they will immediately get notified in the jack if there is a loss of that elongation, not increase of elongation with time. It does not happen. It is a loss. And that is the reason why people wait for 24 hours. They see that the wedges are not slipping or strands are not slipping into the wedges. Then they say, fine, it will not slip any further. But I've seen cases where they slipped afterwards also. There have been cases, but they are very like one in thousands kind of cases.
Right.
So it is assumed that 99% would be fine if I wait for 24 hours and then cut the strands and grout.
Right. How is the quality, Arun has asked, how is the quality of water maintained for grout preparation?
For grout, what is done, there are several tests we carry out on the grout. And the tests are for the air content in the grout. The tests are for this, what do you call it, slump in the grout. And the tests are for volume change of the grout.
Yes.
So there are 4 or 5 tests, some family of tests which are carried out.
Where might he find them? Probably he's unaware. He wants to know where to find out all these matters.
If you remember one of my slides, I can show you there is a code number mentioned, EN. Two codes are mentioned in that slide.
EN is European code, yeah?
European codes,
EN.
yes. Okay. Indian codes, I don't think have much about it at the moment.
Alok, anything?
No, I think what Vinay said, I will just echo the same thing. Yeah. So there is a Euro code.
445
I think that
457, it's on your slide.
And that finds a mention in IRC 112 also in the section 18 of the where we talk about grouting. There is a mention, I think, of that Euro code.
So precisely the code numbers are EN 445 and EN 447.
I was not wrong. I remember that slide. Okay, there you go. Now, excellent presentation, Jagannath Rao. Again, commend you. That covered not only critical design aspects, also constructivity aspects. Thank you. Jagannath Rao, thanks for your praise. It spurs us on to do more and to share more knowledge. So we will try and do better.
Thank you, Mr. Jagannath.
We will try and do better even next time. Can you elaborate more on hyperstatic effects? We have a bridge system, the PRESTRESS 25, 35, 20 meter continuous integral system. What problems will be there in pre-stressing? This is Nadaf, Irshad Nadaf asking. Yeah.
See, hyperstatic system is nothing very great. It's only that people may forget or may not realize when they size the pre-stressing. You have a continuous structure which is indeterminate. You apply a force somewhere, it has an effect elsewhere as well. That's all we do. So for hyperstatic effect, If you take a 3-span or 4-span or whatever continuous structure and simply apply a force equivalent of the pre-stressing, even in a simple software, or I don't know if you can do manually, I'm not very certain, we will get effects on the other spans. Now, this is a real effect. It's not time dependent, it's real. But what is time dependent hyperstatic? I can also tell you that. You have losses in the pre-stress. These losses also get into hyperstatic mode because it's a continuous structure when it's continuous. So that little effect is also taken into account. When you do it in the software, you know blindly you think everything is done and actually is done, but something may be missed out. So hyperstatic is nothing but you provide a force somewhere. It's like something like applying a vertical load. It does not give you W squared by 8. It gives you lesser because rest of it has gone to the support and the other span very much the same way. The axial force that you apply at a particular location, not axial, rather axial force with eccentricity, it converts into a distribution into other spans and supports. That's all about hypostatic.
Right. Uh, some very quick questions because we are running out of time more or less, and I'd like to close in a few minutes and ask Alok to then sum up. Venkatesh asks, Mosale Venkat, using a hydrogen-based grout, is there a possibility of hydrogen embrittlement to occur onto the pre-stressing? Is there any danger of hydrogen embrittlement using a hydrogen-based grout? I'm not sure what that kind of grout is.
I really do not know about it.
Is there the risk of hydrogen embrittlement in any case that may accrue because of the wrong use of a grout or some compounds or deleterious agents in the grout, or some chloride impact due to some accelerator or something that may be used in the grout setting? Well, you'll have to test that. Whatever you used should be tested. It's as simple as that. You don't introduce something without testing. So if the grout mix has to be tested for all the various issues before it's used for sure.
There's a total limit of chlorides and sulfuric anhydrides in the grout, which I showed one slide.
Right.
Anything you do must follow that.
Syed Amin asks, if pre-tensioning is used, if the pre-tension is cut by a hand grinder, does the sudden impact of the release of pre-stress cause concrete cracking at that zone? You cut a grinder, does it have a sudden impact issue and cause cracking of the concrete?
Are you talking about pre-tensioning?
In pre-tensioning.
Okay, in pre-tensioning, what happens, the provisions are very clear. You're allowed to use flame to cut the strands, so slowly the force is released. You're allowed to do a saw cutting, but strand by strand and symmetrically from the transfer center.
Right.
So if you have, let's say, in the case I showed 40 strands, in the case of Delhi Gurgaon, if you're cutting one strand at a time, it's only about 2.5%. Right. Only thing you go symmetrical transversely. So it is not an impact.
Right. So you have to consider the pattern in which you would go, and you have to do it gradually and not all at one time. And it is easily controlled, right?
Yes.
Which grade of concrete are you suggesting in heavy loading bridges? We are using M50 concrete right now. We are using. Ramlingan Sundarajan asks, can we use higher strength concrete? So should we use, or what compatible with pre-stressing? Are we getting some benefit? I'll extend the question. Are there advantages to using higher strength concrete like M60 and beyond for pre-stressed concrete bridges which are heavily loaded? Is there any?
See, when we use richer concrete, say M60, M70, M80, one advantage we have is a durability, because richer concrete is more compact, more dense, and has a better weathering resistance to the steel. Other is that if you have a larger span, where the control of the compressive stress is important, and it is of course important, but more important, then the code has now extended to give you a larger permissible compressive stress as well as larger shear stress. Now, earlier it was not the case. They were limiting it to 40 or 50, 40 MPa, 45 MPa. So with these things, once you have a larger span and you want to restrict the section for various reasons, it is economy, it is carbon footprint, greenhouse effect, whatever you call it, or aesthetics, then it's better to use a larger strength concrete. Like I'll give an example. In this Panjakota flyover in Hyderabad, they've used M60 concrete using microsilica throughout.
Yes.
Whereas these are regular spans of 40 meters and all that. In the case of JJ Hospital,
yes,
they have used M75 concrete.
Yeah, and 60 and 75.
All the spans are not very large, but they wanted to minimize on the section thicknesses. So it's purely that. But any engineer, any designer, any contractor can make a calculations of economics, and you can decide accordingly also. So these are various regions and factors based on which you're an engineer, you decide
Right. Elastic shortening loss in any cable or only in second stage pre-stressing? In all cables or only in second stage pre-stressing cable? Elastic shortening loss.
Okay.
That is Lalan Mishra has asked it.
Okay. I'll take an example that we have a girder, any kind, box girder, eye girder, and we put only one cable. This one cable also will exert axial or longitudinal compression in the girder. And once a compression is created, the concrete has to shorten. So elastic shortening will take place right from first girder, first cable itself. When you put a second cable, it has an effect on the concrete and also relieving effect on the previous cable. That's a obvious matter. But any one cable will give an elastic shortening effect on the concrete due to the compression it creates.
Yes. What is the specification of grouting admixture used for grouting purposes as per EN or ASTM standard? The grouting admixtures, are there any specifications for them?
Yes. Again, they are given in that EN 445 and 447 as to the specifications which are for making it stable against bleeding, and also and another one is for making it having a better slump for it to flow properly like a paste or like a thin paste.
Right. Is pre-stressing used in masonry structures? Can it be used to retrofit applications? Piyush Singh is asking.
We have used it.
Yeah, you
in
can
the
use
retrofitting.
it. In fact, you can use it to retrofit timber, masonry, steel. There is a steel code, IRC steel code already for pre-stressed steel structures. I was involved with that. And the issue of masonry structures you use to you can use your normal CFRP or GFRP laminates and fabrics, etc., which can be discretized and put and buried, and you can get the get up again. It is largely used. There's no problem. Used worldwide for masonry retrofitting because it is inert. The other benefit, it's an inert product, so it doesn't interfere with the natural process of the breathing and that of the masonry structure, and it can give some additional resistance. Okay. Epoxy versus dry joint, Surajit Chakrabarti, we have done that. Is there any limitation for percentage of debonded strands? If you debond, is there any limitation on how much you can? Madan Mohan is asking.
Yes. As of now, our code is a bit silent about this fact or this limitation, but ASTO code has given a limit that not more than 25% of the strands must be debonded at a location. So we are still trying to see whether to bring this in here or not, because then we have to see the practical difficulty as well.
Yeah.
And we have to understand what is the theoretical rationale behind it.
Yeah.
So, but as of now, IRC code does not have a limit. International codes, at least ASTO does.
Yeah. So there is a limit in ASTO, not in our code at the moment. We are considering to put it in or not. That debate is on in the committee.
Vinay, I think it is there.
Have you brought it in?
Yeah.
How much is the limit?
33%, I think.
Yeah.
If I remember correctly.
It must be a recent development.
Yeah.
In that case. Okay.
Just have a look. If you have the clause number, we could give the.
I think you go on further. In the meantime, I'm trying to find it out.
So Sunil Khan, whose father was legendary CV Khan and the CV Khan company.
Right.
So Sunil, a dear friend, is asking: are there any measurement methods for loss of pre-stressing using embedded sensors that are in place during construction/maintenance? Loss of pre-stress, can we embed some sensors to understand its progressive loss with time? Is there any method of knowing that? Yes, you do have load cells which are now available and are instrumented into the anchorage blocks itself, and that will give you a global issue of the loss of pre-stress in that particular cable. There are various indirect methods, Sunil. Of course, you know the trepanning method, the so-called trepanning method. Like that, there's the Gifford system. There are so many systems in which we can make a hole in the concrete, a core cut a hole, and maintain the relief of stresses due to that hole and the increase in the stress concentration around the periphery, and so on, and indirectly measure the strains and then work out the state of stress in the concrete at that location. These are techniques that are available. Either you put in a load cell at the start and you know it a long time, or you post de facto in the structure in service, you can do the street panning method type of concept and infer the change in strain to the state of stress at that point. Yeah.
So in the meantime, it is clause number 4.5 of SP 71 2018.
SP 71,
33%.
not the code. Yeah, SP 71. Yeah.
33%.
Okay. Righto, not 112. Righto. Now, at disturbed zone, usually considered as the depth of the beam of PSC girders near supports, we do not check stresses at SLS. Can we ignore the tensile stresses in the disturbed zone at SLS and check the disturbed zone of PSC girders only under ULS?
Is what that is the disturbed zone?
Jayanth BK. For the depth of the girder, for the depth equal to the depth of the girder, we do not check stress at SLS, only at ULS. Can we do that? Tensile stresses. Is that an issue?
Are we talking about the place which is near the bearings?
Yeah, near the end zone are equal to the depth of the girder. The tensile stresses in this zone, do we check at SLS or at ULS only? That is his question.
As far as direct concrete stresses are concerned, or the steel stresses are also concerned, they are checked everywhere throughout.
Yes.
Right till the support.
Yes.
But if it is shear, then I can understand that yes,
it is only at the
there is an enhanced permissible shear stress near the support.
Yeah.
So on the truss analogy.
Yeah. Sir, Harshvardhan asked, sir, please explain about the decompression check to be done in PSC girder.
In PSC girders, yes. Oh, you want to explain the decompression?
Yeah. What is the decompression check?
It's a very simple effect. Yeah. A very simple effect, though a new entrant in the code which came in 2011, that around the pre-stressing, I mean, how it began, let us understand. People used to say that, look, when it's a RCC, you permit tensions. When it's pre-stress concrete, you say no tensions at all. Why? Why such a disparity? So it came to that, look, pre-stressing has a larger chance of getting corroded or getting affected for durability because it is under higher tension. So that's the reason. But why should I punish the entire structure for that? So fine, they said when we are in a severe or very severe zone of durability class, weathering class, then we say only around the pre-stressing duct within 100 millimeter radius, we should not get, 100 mm layer around the pre-stressing duct, we should not get tensions. The rest of it can have tensions. Only in those zones. In the milder zones, we can have tensions everywhere, limited tensions everywhere in pre-stress concrete. So what we are talking about, decompression is only that around the pre-stressing in the certain zone, we should not have tension. But practically, when you try to escape this, you find that you have to have compression of the concrete anyway, even elsewhere. It doesn't work otherwise. So we'll have to see which is that condition where we can have this zone without tension, but the rest with tension. I really have to see that.
Alok, anything to add? This is a tricky one. That's why I asked. Alok,
it's a more of a software formula.
Yeah. Anything to add, Alok, about this decompression check? I'll take the next one. I can't hear Alok. Unmute.
Yeah, so practically decompression would mean there are two ways you can tackle the issue. One is that means indirectly it is stating that no tension is permitted when you have that kind of an exposure class where you require decompression, and that is, I think, very severe and extreme. Second, if you want to still take some advantage, there can be situation. You see, your pre-stressing cable is at near the edge, only at the critical section, which is mid-span. But other sections, you can have a situation where the cable is quite away from the extreme fiber, where you have a decompression with tension, you can still permit tension. So other than the critical section, you can have a situation where tension can be permitted, provided your cable is up. Or alternatively, the entire CG of the cables you have to move up.
Yes.
So
it looks very theoretical today, but let's see if we find such practical examples where it gives us an advantage.
Yeah. Probably in a situation of like pre-stress segmental bridges, where you need pre-compression in any case.
Right.
I mean, such situations. But then there is no question of decompression there.
Hmm.
I mean, the whole thing is decompressed.
Right. Just few questions and we should wind up. Tarun Mathur asks, can post-tensioning be used in steel truss bridges? Any code covers this? Yes, there's an IRC
Yeah, it
guideline
is.
long ago. And there are
Yeah.
many treatises by Troitsky and Belenia. And the Russians are actually leaders in pre-stressing steel truss bridges and all types of steel bridges. You can find the code. And it has been used also in India on number of projects too, to pre-stress a steel bridge. Yes, a truss or otherwise. Yeah. Jagannath Rao asks, regarding the comment about bridges in high seismic zones, can a tune mass damping system be introduced in bridges in these areas, which is quite common in high-rise buildings in high seismic zones? Can we introduce TMBs in high seismic zones?
Yes.
Or friction pendulum bearings, or
Yes.
what are the STUs? So what is the status at the moment? Vinay, you know best to answer this question.
Yeah. You see, if we talk of friction pendulum dampers, we do have it in Signature Bridge, where I think Dr. Subbarao and us, we are both involved.
Yeah.
If we talk of tune mass dampers are more thought of in the case of cable stayed bridges.
And
so the codes which are under preparation under Mr. Alok Bhamik or Professor Mahesh Tandon, in those codes are under preparation now. There, the talk of tune mass damper is there for long spans, for cable stayed bridges especially. So they are under use. I mean, internationally they are being used. In India, we tend to use them for vibration control.
Yes.
Yeah.
And TMDs, especially for wind sensitive, before you close a cable stay at its maximum span, just before you close it, that is when at the maximum cantilever it is most, prone to wind-induced, very high wind-induced movement. If you forget about it, high movements caused by wind of different types. So then is where we introduce a tune mass damper to ameliorate the kind of movements that would accrue otherwise. So what will be the maximum length of stand in a pre-tension girder? Can it be 500 meters or 1 kilometer? The bed, how long can the cable be in a bed?
See, one is a span, other is the length of the bed. Now, length of the bed will be more governed by the limitation of the jack, number one, how much it can elongate. Usually one has seen a maximum of 600 mm elongation in the stroke of the jack. And therefore the limit on the strand that is normally put is about 100 meters practically. The other problem that will come is that if the length of the whole thing is too large, then when the strand is released, the strand moves because it's a long one. So it moves back. The whole girder will be moving maybe a meter, meter and a half and all that we can't afford. They will hit the other girder or something else will go wrong with the bed and they'll have cracks at the bottom. So to avoid this, there's a practical limit. Theoretically none. Yes. That's about the length of the length of the bed. But if we talk of the span, if that was the question, then in the case of span, there's a practical limit. It will be about 40 meters or so. Beyond that, the girder has to be very deep to see that with this pre-stressing all at the bottom straight line, it still is designable in terms of the tensions and compression, of course. And in most cases, it spans about 20-25 meters. We do require top strands also to control the tensions at the top. But when it goes beyond 40 meters, it may become difficult to control this part because we can't curve the cables. Internationally, outside India, people do curve. They have a special arrangement through which you can still anchor and curve the cable, but strands. But in India, we don't have that.
We don't do that. Yeah. Okay. Very good. The practical limitation. Also, the transportability of a length of a span would come in. Height and transportable length. Yeah.
Yes.
Amit Gupta, thanks you again for introducing him back to the basics and design construction issues. So does Gaurav Kaushik. My compliments to Vinay Gupta were well deserved for a very well delivered presentation. Kudos to Mr. Alok Bhaumik and Dr. Subbarao for the excellent Q&A session. Please keep up the good work. Yes, Alok, this is enough credit for you and Vinay. We have with you three associations. I mean, we have there's Vinay Gupta, president of IIB and also the Indian Concrete Institute. And here is Mr. Alok Bhaumik, the president of the IS Trustee, and yours truly, some sort of vice president of some other bodies. So yes, we will try and do something very much in keeping with this. Your feedbacks are important for us to know what sort of areas you would like us to focus on, be it in buildings, bridges, special structures, whether you want it at a level of knowledge sharing or whether you want it particular topics to be addressed. These are all the things which we would, it's a design aspect, a construction aspect, a repair, rehabilitation, maintenance aspect. Any of these things you can flag up and we try and do our best to put something together for you and share it with you. Okay. Mr. Sun, so on that note, Alok, there are so many questions. They are unending. So
I think we have to close it now.
Yeah.
We are fading
Alok,
now.
can I ask you to?
So I would like to.
One last statement from the speaker.
Right, go ahead.
Yeah, sure.
So friends, I see about 129 people, all of you and us. We live bridges, we sleep bridges, and we practice bridges.
Okay. Thank you, Vinay, for this excellent presentation. Very illuminating lecture, and I think the participation by all the participants by Q&A reveals that people have really liked your presentation. Thank you very much, and I profusely thank Dr. Subbarao also for excellent. You have become a professional moderator, I can tell you. You have done an excellent job, Harsha, and I think now we don't have to look for anybody else to moderate. All our lectures moderated by Harshavardhan Subbarao. Before I close, I just want to mention that we have two more webinars which is scheduled for 16th of January. One day, but there are two webinars by IAS Shakti. One in the morning, which is on advanced wind tunnel testing techniques, part 3. We have already, had two parts. Now this is the third part on long span roof structures. And I would request all to kindly sort of spare you block your calendar for 16th of January because you have two webinars, very interesting ones. The first one I mentioned, advanced wind tunnel testing techniques, part 3, long span roof structures. And the second one is even more interesting, which is on structural engineering for sustainable development. And that will be a unique webinar, which is all women webinar, where we have four panelists, Dr. Anil Sheth, Dr. Shilpa Paul, Dr. T. Visalakshi, who is the Secretary of Indian Association of Structural Engineers, and we have Miss Anamika Kadam. She is from L&T. So four women will be speaking on sustainable development, and this will be moderated by our Secretary, Dr. T. Visalakshi. And I think we all should participate in good numbers in both these webinars. With that, I close this session.
One announcement, Alok. One announcement
sure,
before you officially close. Ladies and gentlemen, there's high load disc bearings are very much used in bridges and other civil engineering structures. It's Watson bearing is a world famous bearing, less understood by us as Indians, and the do's and don'ts and where they have been used and why and how they're better or worse. These will be the topic of debate on the 8th of January. IIB will have a discussion. Vinay, would you like to just say one or two words before Alok closes the session? Yeah.
Yes, I think I'll inform everybody that we had some presentation on bearings about 2 weeks ago. And the presenter somehow said that disc bearings have their own disadvantages and all that. And somebody contested. So when this somebody contested, we said, fine, because we've heard of disc bearings as a very efficient set of bearings, especially used in Worli Bandra ceiling and all. So let us hear from you and let us then analyze. Because it's all a debate, everybody has his own personal views. So idea was to let's have this debate. Let us understand the merits and demerits of disc bearing vis-a-vis the merits and demerits of what we heard the other day, which is, let's say, friction pendulum bearing or whatever bearings. So that is how we are having this presentation by the Watson. I think the person is from somewhere in Europe, I've forgotten. So we'll have this presentation
from
and
America.
please.
America, yeah.
From America. Yes. Oh, he's agreed for a very early. He has to wake up at 5:30 in the morning.
5 o'clock in the morning.
Yes. So please do attend. At least let us understand. I also do not know very much about disc bearings, but I only know that they entail a very small size. They can take a very high load, and let us
Very high
understand how
rotation.
much lateral force and all they can take, rotation they can take.
In fact,
Like that.
the disc bearing, the world authority in disc bearings, Ronald Watson will be speaking. He owns Watson. He patented disc bearing. I
Same
mean,
person,
he's the
yes.
same person who's going to be speaking.
Right, right.
I think
right.
his
The world
father.
authority.
I think his father patented
His
it.
father,
It
yeah,
could be
father.
father and son, yes.
Yeah, they're company.
So it's going to be very interesting for knowledge sake.
And
Yeah.
moderated by
Finally,
Atul
decide
Bobe and
whether
other
we want to use
stalwart
it on, it
executives.
is a separate matter. But at least for knowledge, it will be very good.
Yeah.
Yeah, I think I must thank Vinay for organizing this on disc bearing. It was very nice of you, because
In
that will
fact,
be
we
very
have never
interesting.
discussed this
We never
bearing. So this
discussed
time we
it.
And
will for the first time.
I think I mean, with this online thing has helped us to sort of reduce this distance, and now we
Yes.
can think of having a presentation by RJ Watson himself. I mean,
That's right.
unbelievable.
That's right. That's
So
right.
that's great. That's great.
Absolutely.
We
He
look
said it.
forward to 8th of January for this presentation. And my request, Vinay, kindly invite our convener of B6 committee also
Yes.
for
Okay, okay. Right.
for
Mr.
that
Puri.
Mr. SK
Ask him
Puri
to
SK Puri.
panel. We'll put him
as
on the panel.
in the panel.
Okay,
We'll do
I'll try
that.
to remember. I may
Yeah,
forget.
yeah.
Yeah.
I'll do that.
And it
Thank
would
you
be
for that.
very nice if you can also invite the speaker that day who spoke about the spherical bearing.
Okay.
I mean, it will be very
Rathod.
useful. No,
Oh,
not Mr.
Rathod.
Rathod.
No, no, let us not do that.
There will be chaos. There will be
No, no, no.
war.
They'll be
It's
fighting.
no. It's a
Right.
technical
Let me
debate.
ask him. Let me ask him.
Yeah, I see nothing wrong in that, because let
Yeah.
there be a fair amount of discussion
And
uh,
consensus.
and consensus. Yeah, yeah.
Righto.
So with that, I once again thank Vinay and Dr. Subbarao,
Thank you.
and
My
I
pleasure.
close this session.
My pleasure.